It was the spring of 1965. On the eve of the first manned missions in the long-developed Project Gemini, when a supervisor at the Jet Propulsion Laboratory, Joe, the acting head of the Advanced Projects Group, approached his team with a challenge. He asked them to conduct an in-depth study of potentially useful outer planet mission profiles and launch opportunities that might become possible in the near future. With the conclusion of the International Geophysical Year almost a decade earlier, the United States had gone head-to-head with the Soviet Union in a robotic race to the moon, and had roundly lost. The allure of the moon, and the promise of dominance in space, proved irresistible. It soon became the primary target of a much more popular foe, much better funded, and far more politically important manned program. Throughout the 1960s, unmanned exploration progressed largely in a supporting role. Missions such as Ranger and Lunar Orbiter were essentially scouting expeditions, reconnaissance missions designed to prepare the way for the Apollo landings. Yet the possibility of journeys to other planets captivated scientists and engineers in a way that almost nothing else could. Except perhaps the Apollo missions themselves. That dream soon emerged as the next logical evolution of the unmanned exploration program. In retrospect, there is often a tendency to inflate the perceived scientific focus of unmanned missions when they are compared with the political and technological objectives that drove human spaceflight. This argument is frequently used to downplay the scientific achievements of manned missions in favor of robotic exploration, which is often described as being more scientifically pure in both design and intent. But despite the genuine importance of studies in magnetospheric physics and planetary gravimetry, the truth is far simpler. What truly captured the imagination of the American public was the promise of photographs, images of distant planets, worlds that had never before been seen up close, were the spark that ignited public fascination and helped propel unmanned exploration forward through what would later be called the golden age of spaceflight. It was within this atmosphere of curiosity, ambition, and competition that the United States and the Soviet Union opened an entirely new chapter in their rivalry for space. Above the atmosphere, a new race was beginning. A race to the planets. This was also the first race in which the Soviet Union had experienced a clear defeat. The American spacecraft Mariner 2 successfully reached Venus in December of 1962, marking a major milestone for the United States in deep space exploration. By 1965, when Gary Flandreau and his colleagues, working as part of Joe Kewing's team, were tasked with studying near-future opportunities for missions to the outer planets, the next step seemed almost obvious. The space race had gathered unstoppable momentum. Each year, budgets increased, ambitions expanded, expectations grew. Yet in 1965, it was still unlikely that the unmanned program would receive rockets powerful enough to send spacecraft to the outer planets. Exploring those distant worlds was, in many ways, an entirely different challenge, a completely new level of difficulty. To understand why, imagine a simple solar system. Several planets orbit a star at the center. The planets that lie closer to the star feel its gravity more strongly, which causes them to orbit much faster. Planets that lie farther away must travel a much greater distance along their orbital paths. But because the star's gravity is weaker at those distances, they also move more slowly. For interplanetary travel, minimizing fuel consumption is the most important goal. Gravity and velocity dominate every decision in trajectory planning. If you want to travel from the innermost planet to the outermost planet, you cannot simply point your spacecraft and go. Instead, you wait. You allow the planets to continue moving in their orbits around the Sun until they reach a specific alignment with one another. When that alignment occurs, you launch. This moment is known as a launch window. At the right moment, a spacecraft can accelerate away from Earth, then coast outward through space, aiming for a point slightly ahead of the planet it is trying to reach. If the trajectory is calculated with enough precision, and with a little luck, the spacecraft will pass close enough to the target planet to fall into its gravitational well. Transfer windows between Earth and the other planets in our solar system occur fairly often. At least once every relative year there is an opportunity of some kind. So in that sense, they are not especially rare. But Joe Queuing, Gary Flandreau's supervisor, was studying something more sophisticated. He was exploring the possibility of using an intermediate planetary gravity assist in mission profiles designed to reach Mercury by way of Venus. You can think of this as a double transfer window. First, a spacecraft would launch from Earth and travel to Venus during a favorable Earth to Venus alignment. Then, by the time it arrived at Venus, another transfer opportunity would already exist between Venus and Mercury. Instead of relying on a powerful engine burn, the spacecraft could use the gravity of Venus to bend its trajectory in exactly the right direction. In effect, Venus would act like a cosmic slingshot, redirecting the spacecraft toward Mercury, because the spacecraft would already be traveling at escape velocity when it arrived. No massive additional burn would be required. Gravity itself would do most of the work. The spacecraft would already be arriving at Venus at escape velocity, carrying far too much energy for Venus's gravity to capture it on its own. Instead, that gravity could be used to redirect the spacecraft's path. This concept would later lead to the highly successful Mariner 10 mission in 1973. The idea behind a gravity assist was actually quite simple. In order to minimize the amount of rocket fuel needed to push an exploration payload, such as a robotic probe, engineers could take advantage of the gravity of an intermediate planet. If that planet's gravity could bend the outbound trajectory of the spacecraft toward its final destination, it would dramatically reduce the amount of fuel required. That meant less weight, lower launch costs, and much more ambitious missions. In 1965, this strategy was considered absolutely critical for success, because NASA's rockets still had very limited lifting capability. A method for shaping trajectories using planetary gravity might therefore make missions to the outer planets possible. Gary Flandreau began exploring this possibility early on. Much of the theoretical groundwork had already been laid by earlier scientists. Among them was the German rocket engineer Walter Hohmann, as well as astronomers and mathematicians from the Copernican era, including Johannes Kepler. These scientists understood that planetary gravity fields could perturb the orbital paths of objects such as comets. By graphing the heliocentric positions of the planets and analyzing their long-term orbital patterns, Flandreau was able to make remarkably accurate predictions about where the planets would be positioned in the future. As he studied the data, he realized something extraordinary. Just before the 1980s, there would be a rare quadruple convergence. This alignment occurs only once every 176 years. During that brief period, all four gas giants would appear on the same side of the Sun and in the proper relative positions to allow a spacecraft to perform multiple gravity assists in sequence. A single probe launched toward Jupiter sometime in the mid-1970s, with an unprecedented level of navigational precision, could theoretically swing past Jupiter, then Saturn, then Uranus, and finally Neptune. And it could do all of this without requiring major fuel burns after leaving Earth orbit. The original boost from Earth would provide the energy needed. After that, gravity itself would guide the journey. The realization of this remarkable opportunity began on the third floor of Building 180 at the Jet Propulsion Laboratory during the summer of 1965. In an extraordinary coincidence, the planetary alignment would not occur for more than a decade. That delay provided just enough time to design the mission, secure funding, and build the spacecraft needed to attempt it. Of course, that would only happen if the mission concept was approved. The proposed exploration profile soon became known as the Grand Tour. Interest in the idea grew rapidly after 1966, when Gary Flandreau publicly published his findings. In that paper, he outlined several possible mission profiles. Two of them quickly emerged as the most promising. There were several major constraints. The first, of course, it was delta V, the amount of speed required to achieve such a complex trajectory. This depended on two factors. One was the weight and complexity of the probe itself. The other was the power of the launch vehicle that would carry it into space. The key idea was to take advantage of free energy whenever possible. Instead of relying entirely on rocket propulsion, engineers could use gravitational energy already present in the solar system. As Jupiter moves along its orbit around the Sun, its enormous gravity field can pull a passing spacecraft forward. This technique is known as a gravity assist. A gravity assist can provide an enormous boost of energy. In fact, the increase in velocity can be equivalent to the thrust of roughly 4 Saturn V rockets waiting for you out in space. If you could harness that boost, a spacecraft could dramatically increase its speed without burning additional fuel. After passing Jupiter, the probe could then head towards Saturn. There, another gravity assist would provide yet another powerful boost. From Saturn, the spacecraft could continue outward toward Uranus, and then onward to Neptune. Beyond Neptune, the spacecraft would begin its long journey out of the solar system itself. At that point, it would enter the vast region of interstellar space. But there was another important challenge: convincing people that such a mission was worth attempting. At first glance, the idea sounded almost impossible. Gary Flandreau himself later recalled wondering how anyone could ever persuade decision-makers to support such an ambitious plan. The key to gaining approval was to demonstrate that meaningful scientific discoveries would occur within a relatively short period of time. In particular, the mission needed to produce major results within about 4 years after launch. The second major constraint was time. This would not be a typical mission lasting a few months or even a few years. Instead, it would be a journey lasting more than a decade, and possibly far longer. Gary Flandreau, who was still a student when he made the discovery of the planetary alignment, would eventually leave the Jet Propulsion Laboratory long before his vision was fully realized. Another important advocate soon emerged: Dr. James Van Allen, the same scientist whose instruments aboard America's first satellite, Explorer-1, discovered the radiation belts surrounding Earth. Those belts would later be named the Van Allen radiation belts in his honor. Van Allen became a passionate supporter of exploration of the outer solar system. At the time, NASA was facing shifting priorities and growing budget pressures. Public enthusiasm for the Apollo program was beginning to fade, but the idea of larger and more ambitious robotic missions, capable of exploring distant worlds at a fraction of the cost of human spaceflight, began to look increasingly attractive. This idea proved appealing to the Nixon administration, which was eager to establish a new direction for American spaceflight. The new administration wanted to move away from the vision that had defined the Kennedy and Johnson years. During this period, the scope of the Grand Tour project fluctuated dramatically. At one point, engineers at the Jet Propulsion Laboratory even considered launching 4 separate but identical spacecraft in order to fully exploit the incredibly rare planetary alignment. However, inside NASA, these ambitious proposals soon found themselves competing for funding with another major project that had just been approved: the Space Shuttle. NASA leadership was slow to embrace the Grand Tour concept. The agency already had its own outer planet exploration missions underway, developed by an entirely different team. These were the Pioneer missions. For the first time in history, spacecraft were reaching planets that had once been considered far beyond humanity's reach. Pioneer 10 and Pioneer 11 were both designed to fly past Jupiter using the newly developed concept of gravity assist. Pioneer 11 would later continue on and perform a flyby of Saturn. Aside from a single onboard scientific instrument contributed by the Jet Propulsion Laboratory, JPL itself had little involvement in these missions. Gradually, the novelty of the Grand Tour concept began to fade. Ironically, its very goals were being partially achieved by another American robotic exploration team. In 1971, the original 4-mission, 4-planet Grand Tour concept was officially rejected. The following year, in 1972, NASA approved a different program entirely. It was called the Mariner Jupiter-Saturn mission. The plan involved 2 identical spacecraft. Both would fly past the 5th and 6th planets from the Sun, Jupiter and Saturn. In many ways, it appeared to be little more than an extension of the earlier Pioneer 10 and Pioneer 11 missions. But NASA saw it differently. The Pioneer probes were relatively small and technologically simple. They were designed primarily as reconnaissance missions. Their purpose was to gather basic information and open the door for more advanced exploration. The Mariner Jupiter-Saturn spacecraft would be very different. The probes developed by the Jet Propulsion Laboratory would be more than 3 times heavier than the Pioneer spacecraft. They would also carry a far more sophisticated set of scientific instruments. NASA planned to use these probes to revisit Jupiter and Saturn and conduct far more detailed studies of these enormous worlds. There was, however, a remarkable twist. These new spacecraft would launch in the late 1970s, exactly during the rare planetary alignment that made the Grand Tour possible. Yet NASA had no official plan to take advantage of that alignment. Every new discovery we make adds to the foundation of knowledge that future explorers will build upon, even if we cannot yet see where that knowledge will lead. Just because we cannot see where the future leads does not mean it is not there. If we refuse to take bold steps simply because we cannot predict the outcome, the only thing we guarantee is that the future will never arrive. Human progress would stall. We would stagnate forever. And that is a deeply troubling thought. I often grow tired when people ask a simple question. What is the point of all of this? The honest answer is that you may never know. But your grandchildren might. Despite the limited official goals of the new missions, which were primarily intended to use Gary Flandreau's late 1970s launch windows to reach Jupiter and Saturn, a quiet culture of stubborn persistence began to grow at the Jet Propulsion Laboratory. Even with limited funding, the engineers at JPL had every intention of designing spacecraft that could survive long after their encounter with Saturn. Officially, NASA had no plans to continue the mission beyond Saturn. But unofficially, many of the engineers believed something else might be possible. During the design and construction of the spacecraft, an unspoken understanding developed between the engineers and the scientists working on the project. Quietly, without public discussion, they began to consider the possibility that the spacecraft might continue farther. If the probes remained healthy after Saturn, they might attempt a flyby of Uranus. And if everything continued to work, perhaps even Neptune. By 1972, the mission had been officially scaled back. It was renamed MJS-77, which stood for Mariner Jupiter Saturn 1977. The official objective was simple. 2 spacecraft would be launched to study Jupiter and Saturn, along with their moons and their magnificent ring systems. Fortunately, the launch date remained set for 1977, and that timing meant something remarkable. If the spacecraft continued to operate after the Saturn encounter, they would still be in position to travel onward to Uranus, and eventually even Neptune. In that case, the mission could complete the original vision of the Grand Tour of the outer planets, a journey that would take about 12 years. Without that rare planetary alignment, such a journey would normally require almost 30 years. So even though the Grand Tour had been officially rejected, the idea itself was not dead. Slowly, quietly, it began to return. Not through any top-down decision from NASA management, but through the determination and quiet ingenuity of the engineers and scientists working at the Jet Propulsion Laboratory. What eventually emerged was something close to a quiet, bottom-up effort. Almost a kind of informal conspiracy among those who deeply believed in the importance of such a mission. Slowly, year after year, additional objectives were quietly added to the plan. Piece by piece, the mission grew far beyond its original scope. Regardless of which scientific instruments or objectives the wider scientific community recommended for the Mariner Jupiter-Saturn mission, the engineers at the Jet Propulsion Laboratory insisted on one thing from the very beginning: television cameras. Photography would be a central element of these flights. In fact, a slightly longer trajectory was deliberately selected in order to provide the best possible lighting conditions for photography during the encounters with Jupiter and Saturn. Wherever possible, the spacecraft design drew upon the experience gained from earlier Mariner missions. Existing systems were reused when practical, and new subsystems were incorporated from technologies being developed for the Viking orbiters. The team also requested that the Atomic Energy Commission improve the plutonium-powered radioisotope thermoelectric generators. The goal was to ensure that the power systems could continue operating for more than 10 years. Engineers also developed a reprogrammable onboard computer. This capability would prove essential if the spacecraft were to continue operating far beyond their originally planned mission duration. Meanwhile, other missions were already paving the way. Pioneer 10 crossed the asteroid belt in late 1972 and arrived at Jupiter in November of 1973. The spacecraft passed Jupiter at a distance of 132,000 kilometers, or about 71,000 nautical miles. It became the first human-made object to encounter the gas giant, and it transmitted the first detailed photographs of Jupiter ever seen by humanity. But the mission also revealed something unexpected. The radiation environment around Jupiter was far more intense than scientists had predicted. Measurements showed radiation levels nearly 1,000 times stronger than anticipated. This extreme radiation was produced by Jupiter's enormous magnetic field. Pioneer 11 encountered Jupiter 1 year later. After its flyby, the spacecraft began a long and lonely journey toward Saturn. It would not reach Saturn until 1979. Well after the launch of the two spacecraft being developed at the Jet Propulsion Laboratory, the discoveries made by Pioneer 10 at Jupiter had a profound impact on the design of the Mariner Jupiter-Saturn spacecraft. Because the radiation environment was so much harsher than expected, some scientific experiments originally planned for the mission were removed. Others were added in response to the new data. In the end, the mission would include 11 major areas of scientific investigation. These included imaging systems, radio science experiments, infrared spectroscopy, ultraviolet spectroscopy, and magnetometry. The spacecraft would also study charged particles, cosmic rays, and perform photopolarimetry. Photopolarimetry is the measurement of the intensity and polarization of reflected light, such as the light scattered by clouds in a planetary atmosphere. Additional investigations would focus on planetary radio astronomy, plasma environments, and the distribution of particulate matter in space. Each of these scientific fields had its own principal investigator. The heads of the imaging and radio science groups were designated as overall team leaders. The position of lead project scientist was given to Ed Stone, a magnetospheric physicist from the California Institute of Technology who had been working on the Grand Tour concept since 1970. Stone understood very well how strongly public interest influenced space exploration, and how space exploration in turn inspired the public. He firmly believed that communication and public engagement were essential parts of the mission. Very early in the project, he made an important decision. Whenever new scientific discoveries were made, the results would be quickly summarized and shared with the public. At the core of the spacecraft was a structural framework known as the bus. The bus formed the central body of the spacecraft. It was built as a large 10-sided box that housed most of the spacecraft's electronics and internal systems. Mounted on top of this structure, along what engineers called the Z-axis, was the spacecraft's high-gain antenna. The spacecraft was designed to rotate slowly around this axis. Small thrusters attached to the bus provided the control needed to perform this rotation. Each of the 10 sides of the bus contained a small compartment that housed different electronic assemblies. Several external components were also attached to the bus, each serving a specific purpose. One of the most important structures was the science boom. This boom supported 3 instruments dedicated to studying energetic particles in space. These included the cosmic ray instrument, the plasma science instrument, and the low-energy charged particle detector. At the end of the science boom was a movable platform that carried the spacecraft's optical sensing instruments. Among these instruments was one of the most important systems on the spacecraft, the imaging science subsystem. This system consisted of 2 black and white television cameras. They were modified versions of the slow-scan Vidicon cameras that had been used successfully on earlier Mariner missions. Also mounted on the platform was the photopolarimeter. This instrument was a small telescope equipped with polarizing filters. It allowed scientists to study atmospheric particles and to search for evidence of lightning and auroras on distant planets. Another major instrument was the infrared interferometer, spectrometer, and radiometer, commonly known as IRIS. IRIS was designed to measure temperature profiles in the atmospheres of the outer planets. It could also identify the chemical elements present in those atmospheres and measure how much sunlight the planets reflected back into space. In addition, the spacecraft carried a specialized ultraviolet spectrometer. On the opposite side of the spacecraft extended a long fiberglass boom, measuring 43 feet in length. Engineers nicknamed it the astromast. At the end of this boom were the spacecraft's magnetometers. The long distance between the instruments and the spacecraft body ensured that the magnetic fields generated by onboard electronics would not interfere with the measurements. Below the main body of the spacecraft was another smaller boom. This boom held the spacecraft's power system. 3 radioisotope thermoelectric generators were mounted in a line. Each of them was powered by plutonium-238. The fuel source consisted of small pellets that released alpha particles. These particles are essentially bare helium nuclei. As they are emitted, they strike the inner surface of their containers. The impact generates heat. That heat is then converted into electricity through an array of thermocouples, which power the spacecraft and all of its onboard systems. At the beginning of the mission, the 3 generators together produced about 470 watts of electrical power. Over time, however, the output would slowly decline. The deterioration of wires, thermal contacts, and the gradual decay of the radioactive fuel itself would steadily reduce the amount of available power. The high-gain antenna was capable of transmitting data in both X-band and S-band frequencies. Scientific data could also be stored onboard for later transmission using a digital tape recorder. This recorder used a belt-driven mechanism with a reel of magnetic tape measuring 328 meters in length and 12.5 millimeters in width. The tape recorded data across 8 separate tracks. It could record at a high data rate of 115.2 kilobits per second and at a lower data rate of 7.2 kilobits per second. There is some disagreement among historical sources about exactly how much data the tape recorder could hold. In addition, the effective storage capacity would slowly decrease over time because of tape errors and the gradual aging of the hardware. At launch, it is believed that the tape recording system could store about 536 million bits of information. That is roughly equivalent to about 67 megabytes. In practical terms, This meant the system could store approximately 100 full-resolution photographs before the data needed to be transmitted back to Earth. Two whip antennas extended outward near the radioisotope generator boom. Their appearance resembled a pair of rabbit ears. These antennas served both the planetary radio astronomy experiment and the plasma wave subsystem. By this point, the spacecraft had become far more advanced than their earlier Mariner predecessors. Their design, capability, and scientific potential were on an entirely different level. Because of this, NASA decided to organize a public competition to select a new and distinctive name for the mission. On March 4, 1977, the name Voyager was officially approved. Later that year, on August 4, 1977, at 12 p.m., NASA released the official press kit announcing the Voyager missions. The spacecraft would launch aboard a Titan IIIe rocket. Also known as the Titan Centaur, this powerful launch vehicle included a cryogenic upper stage and represented a major advancement over earlier rockets. It was far more capable than the Titan, two rockets that had launched the Gemini capsules into orbit during the 1960s. The Titan IIIe was capable of lifting about 155,000 kilograms into low Earth orbit. It could also send payloads of roughly 34,000 pounds on deep space trajectories. This same type of rocket had previously been used to launch the Viking Mars landers in 1975. In the official press kit, NASA finally acknowledged something that had been quietly discussed for years. A possible third objective for Voyager 2 would be a flyby of Uranus. To support that possibility, the spacecraft had been designed with long-term operation in mind. Voyager 2 would actually launch first. At the end of August, if the Titan Centaur rocket achieved its maximum possible performance, the spacecraft might just barely catch the remaining edge of the original Grand Tour launch window discovered by Gary Flandreau. If the spacecraft remained healthy after its encounter with Saturn, a flyby of Uranus could become possible. Voyager 1 would launch 2 weeks later. However, it would take a more fuel-efficient and shorter trajectory to Jupiter. Because of that trajectory, Voyager 1 would actually arrive at Jupiter about 4 months before Voyager 2. Even though it launched later, one engineer later recalled a remarkable moment just before launch. He believed he was the last person to physically touch the spacecraft. During the final stage of encapsulation, the spacecraft was being sealed inside its launch vehicle. The engineering team had concerns about the delicate windows on one of the scientific instruments. He was allowed to climb inside and perform a final inspection. Part of that inspection involved checking that the small windows covering the instrument's telescopes were properly secured. He carefully gave each one a small twist to make sure it was tight. After launch, the two Voyager spacecraft would reach Saturn about 9 months apart. The mission design included an important contingency plan. If Voyager 1 failed to achieve its Saturn objectives for any reason, Voyager 2 could be redirected to complete those objectives instead. However, doing so would eliminate the possibility of continuing onward to Uranus. This compromise ensured that the primary scientific goals of the mission would still be achieved even if something went wrong. In this sense, Voyager 2 served as a backup for Voyager 1's encounters with both Jupiter and Saturn. But if Voyager 1 successfully completed all of its objectives, Voyager 2 would have another option. It could perform a slightly less valuable flyby of Saturn. That alternative trajectory would allow it to continue outward and attempt a historic encounter with Uranus. Interestingly, Uranus is mentioned 19 times in the official Voyager press kit. Neptune, however, is not mentioned even once. Yet, for those who understood the orbital geometry, Neptune was positioned exactly where it needed to be. If, years later, NASA decided to continue Voyager 2's journey, Neptune would be waiting. Officially, however, There was no acknowledgement of anything resembling the original Grand Tour concept. In total, 3 Voyager spacecraft were actually constructed and given serial numbers, but only 2 were ever intended to launch. The third spacecraft was essentially a partial backup. It consisted of spare components and structural elements that could be used if major system failures occurred before launch. Then, less than 1 month before launch, an unexpected problem appeared. 2 of the 3 onboard computers on the Voyager 2 spacecraft failed. Engineers had to respond quickly. In an improvised decision, the launch order of the spacecraft was switched. The spacecraft originally scheduled to launch second, as Voyager 1 was moved to the earlier launch slot. It would now launch first, under the name Voyager 2. This unexpected change gave NASA and the Jet Propulsion Laboratory about 2 weeks to repair the damaged computers on the other spacecraft. And if that reversed launch order was not confusing enough, history would record an even stranger detail. The physical spacecraft that launched first would be Voyager 2, but the spacecraft that launched second would be Voyager 1. At the last moment, the spacecraft themselves were switched in order to allow time for repairs. NASA also had to swap the radioisotope power generators. Whichever spacecraft launched as Voyager 2 needed to retain the option of continuing its mission beyond Saturn. For that reason, one of the 2 sets of generators was configured to produce a slightly higher output. This adjustment would guarantee a longer operational lifetime for the spacecraft's electrical systems. With that final rearrangement complete, the mission was finally approved for launch. The launch would take place exactly 2 years after the Viking mission to Mars had lifted off. On the morning of launch day, at 10:29 and 45 seconds a.m. Eastern Daylight Time, the 2 massive solid rocket boosters of the Titan Centaur ignited. From that moment forward, there was no turning back. The rocket rose from the launch pad in a column of fire. Within seconds, Mission Control confirmed that the flight was proceeding normally. Telemetry data showed that the launch vehicle was responding exactly as expected. The guidance system reported that everything was on course. The Titan Centaur launch vehicle was an enormous machine, fully fueled. The rocket, spacecraft, and propellant together weighed about 1.4 million pounds. That is just over 635,000 kilograms. During the first phase of powered flight, known as Stage 0, the 2 massive solid rocket boosters provided the majority of the thrust. Together, they produced nearly twice the thrust of the central core stage. For 117 seconds, the boosters burned with tremendous intensity. Their engines expelled the combustion products of a powerful mixture. The fuel consisted of powdered aluminum combined with ammonium perchlorate as the oxidizer. Both components were bound together in a polymer compound to form the solid rocket propellant. As the boosters approached the end of their burn, preparations were made for the next stage of flight, 10 seconds before the solid rocket boosters were scheduled to separate. The 2 liquid-fueled engines of the core stage were ignited. These engines, known as the LR-87 engines, were started in mid-air using a small solid rocket motor cartridge. This ensured a smooth transition between stages. The moment the boosters completed their burn, they were jettisoned from the vehicle. With the boosters gone, the Titan core stage continued the ascent, carrying the Voyager spacecraft steadily higher above Earth. Telemetry from the guidance system confirmed that the vehicle remained perfectly on course. 4 minutes and 20 seconds after launch, staging occurs. The LR-91 single engine ignites and continues pushing the spacecraft higher, faster, and farther toward orbit. 8 minutes after launch, just before reaching orbital insertion, the LR-91 engine runs out of fuel. This is intentional. The third stage of the rocket is designed to perform the most important part of the mission, That stage is the Centaur high-energy upper stage. It is not visible during launch because it is enclosed within the protective fairing along with the spacecraft payload. Unlike the two earlier rocket stages, which used hypergolic liquid propellants, the Centaur stage uses a very different type of engine. It is powered by two RL-10 cryogenic hydrogen-oxygen engines. Much like the early Atlas rockets used during the Mercury program, the Centaur stage is built as a balloon tank. Its structural strength comes from the internal pressure of the fuel stored inside. Because of this design, the walls of the tank are extremely thin. Combined with the very high efficiency of hydrogen fuel, this gives the Centaur stage an exceptional energy-to-weight ratio. The Centaur performs two separate burns. This approach is similar to the S-4B stage used on the Saturn V rocket. The first burn places both the Centaur stage and the Voyager spacecraft into Earth orbit. Then, 42 minutes later, after roughly half of one orbit around Earth, the engines ignite again. The second burn lasts much longer. During this burn, the Centaur accelerates the spacecraft to an extraordinary velocity. The spacecraft gains so much speed that Earth's gravity can no longer hold it. Voyager 2 is now on its way into deep space. But the launch sequence is not quite finished yet. About 1 hour after liftoff, and approximately 12 minutes after the second Centaur burn ends, the Voyager spacecraft separates from the upper stage. Even at this point, however, the spacecraft still needs a little more speed. Attached to the bottom of the Voyager spacecraft is an additional propulsion system. Attached to the bottom of the spacecraft is what engineers call the kick motor. Officially, it is known as the propulsion unit. This stage provides the final, powerful push that sends Voyager onto its outbound trajectory. Because it is a solid rocket stage, it cannot be shut down or throttled once it ignites. It delivers a guaranteed velocity increase of about 2,000 meters per second, or roughly 4,500 miles per hour, to ensure that Voyager does not gain too much speed. The Centaur stage is deliberately shut down slightly earlier than it otherwise would be. By the time the propulsion unit fires and delivers its final boost, Voyager is already perfectly aligned with its intended trajectory. The spacecraft is effectively launched down a narrow corridor of space, achieving an extremely precise insertion onto its interplanetary path. 4 externally mounted reaction control system pods provide attitude control during the chaotic 43-second final burn. These systems draw fuel from the main hydrazine tank located inside the Voyager bus. When the Star 37E solid rocket motor completes its burn and separates, it takes those reaction control system pods with it. Voyager itself carries an additional set of 16 smaller hydrazine maneuvering thrusters. These thrusters are used primarily for attitude control and for small mid-course corrections during the long journey. Once the propulsion unit has separated, Voyager's ability to significantly alter its trajectory becomes extremely limited. From that moment onward, the spacecraft is essentially following the path dictated by the laws of physics. In other words, Isaac Newton is now in control. Each Voyager spacecraft carries about 105 kilograms of hydrazine fuel for its reaction control thrusters. That is roughly 231 pounds. The fuel is pressurized using inert helium gas at about 420 pounds per square inch. 2 weeks pass as Voyager 2 begins its long coasting journey toward Jupiter. Meanwhile, engineers on Earth continue working on the second spacecraft. The flight data computer of Voyager 1 is successfully repaired and reinstalled. However, the guidance computer cannot be repaired. Instead, engineers remove the guidance computer from the third Voyager spacecraft. That third spacecraft had only been built as a structural test model and was never intended to fly. On September 5, 1977, Voyager 1 finally launches and joins its sibling on the journey toward Jupiter. The boost phase of Voyager 1's launch proves to be extremely tense. The LR-91 engine of the Titan III rocket burns for a shorter time than expected. Because of this, the Centaur upper stage must compensate by performing a longer burn. As a result, about 12,200 additional pounds of liquid hydrogen and liquid oxygen fuel are consumed beyond the original plan. It is a nerve-wracking moment for the mission team. At the instant when the second Centaur burn shuts down, engineers estimate that the stage is only about 3.4 seconds away from completely exhausting its propellant supply. If the same failure had occurred during the launch of Voyager 2, the outcome might have been very different, because Voyager 2 followed a more fuel-demanding flight profile. The Centaur stage would likely have exhausted its propellant before the spacecraft reached the proper trajectory. In that case, the solid rocket propulsion unit would not have been able to compensate for the missing velocity. The mission could have been lost before it had truly begun. Yet somehow, by the narrowest of margins, engineers at the Jet Propulsion Laboratory and NASA avoided disaster. Voyager 1 had made it safely onto its path through the solar system. The unmanned Voyager spacecraft were now on their way to Jupiter. Voyager 1 would arrive at the giant planet in March of 1979. Voyager 2 would follow about 4 months later. After Jupiter, both spacecraft would continue onward towards Saturn. At the moment of closest approach to Saturn, on November 12, 1980, Voyager 1 would have traveled approximately 1.4 billion miles through space. Each Voyager spacecraft carries an optical navigation system that allows it to determine its orientation in space. Knowing precisely where the spacecraft is pointing is absolutely critical. A sun sensor mounted near the high-gain antenna allows the probe to locate the sun. Once the sun is detected, the spacecraft can orient itself so that the antenna dish points back toward the inner solar system and therefore toward Earth. The spacecraft body then slowly rolls until 2 star tracking sensors are able to lock onto a known reference star. These star trackers work together in a binocular configuration. They identify stars based on their unique brightness and luminosity patterns. The star most commonly used for this purpose is Canopus. Canopus is one of the brightest stars in the night sky and provides an excellent reference point for celestial navigation. The data from these navigation instruments is processed by the spacecraft's guidance computer. In total, the Voyager spacecraft carry 3 separate onboard computer systems. The guidance computer is known as HiPACE. The name stands for Hybrid Programmable Attitude Control Electronics. This system contains 2 redundant memory banks made using plated wire memory technology. Half of the memory in each bank contains fixed programming. The other half can be reprogrammed from Earth if necessary. HiPACE monitors and controls several key systems. These include the sun sensors, the star trackers, and the movable scan platform located on the science boom. It also controls a small inertial guidance unit. This unit allows the spacecraft to maintain orientation for short periods, even if it temporarily loses its optical lock on the sun or a reference star. A 3-axis gyroscope measures any drift away from the original orientation point. This allows the spacecraft to remember exactly where it was pointing. Such capability is especially useful during scientific observations or when instruments are being calibrated. The scientific data gathered by Voyager's instruments is handled by a second onboard computer. This system is known as the Flight Data System, or FDS. The Flight Data System controls the scientific instruments themselves and prepares the data for transmission back to Earth. All scientific data must eventually be transmitted back to Earth. But during planetary encounters, the Voyager spacecraft will be extremely far away. Because of this distance, most of the spacecraft's activities must be planned and programmed in advance. Decisions such as where to point the cameras, when to activate scientific instruments, when to record measurements, and when to transmit data must all be uploaded to the spacecraft before the encounter begins. Once these instructions are received, Voyager follows them automatically. Like a player piano performing a pre-written piece of music, The spacecraft executes each command precisely, without hesitation and without awareness. Because of this, the responsibility placed on the ground team is enormous. Engineers and scientists must carefully choreograph every movement the spacecraft will make. If even a small error appears in the sequence, the consequences could be permanent. A previously unknown moon might pass by unseen. A rare cloud formation might disappear before an image can be taken. And because the spacecraft will be flying past these planets at tremendous speed, the opportunity to collect valuable data is extremely brief. The critical window is not measured in days. It is measured in hours. The spacecraft arrives, performs its observations, and then the moment is gone. There is a great deal at stake. Both the flight data system and the guidance computer are themselves controlled by another set of computers. These are known as the Computer Command Subsystem, or CCS. Although these computers are built using hardware similar to the high-pace guidance computer, they perform an entirely different role. They store and execute the master command sequences that control the spacecraft. These sequences may include attitude maneuvers, instrument activation schedules, or precisely timed scientific observations. If the guidance and data systems are the instruments of an orchestra, then the Computer Command Subsystem acts as the conductor. Commands sent from Earth travel through the deep space network. This network consists of enormous radio telescopes located at several sites around the world. Through this system, command signals are transmitted to the spacecraft at a rate of about 16 bits per second. Even such a slow transmission speed is enough to control a spacecraft operating billions of miles away. However, there remains a small concern. There was one concern early in the mission. The science boom on Voyager 2 did not appear to have fully latched into place. The proper confirmation signal had never been received. However, there was no indication that the boom was loose or moving. At that point, the team decided to continue monitoring the situation. Just 22 days after launch, Voyager 1 was already 21 million kilometers from Earth. On September 16, 1977, the spacecraft performed an important calibration test. Its cameras captured an image that showed both the Earth and the Moon in a single frame. It would be the last time Voyager 1 would photograph Earth as anything more than a tiny pale blue dot. Through the remainder of 1977, both Voyager spacecraft performed several small trajectory adjustments. These maneuvers were called trajectory correction maneuvers, or TCMs. Using their hydrazine thrusters, the spacecraft executed short bursts designed to correct small navigational errors and refine their paths before the critical encounter with Jupiter. As with nearly every space mission, minor technical issues began to appear during the long cruise phase. These included a small propellant deficit, a bit failure in one of the Computer Command Subsystem computers, and several motors that occasionally stuck. At one point, engineers made the decision to rotate Voyager 2 by 180 degrees. This allowed the spacecraft to lock onto the star Deneb instead of Canopus. The adjustment helped minimize the effects of solar radiation pressure on the spacecraft. Overall, the mission continued to progress normally. Originally, the spacecraft had been scheduled to observe a nearby comet known as Comet Kola. However, this observation was eventually cancelled. Members of the imaging science team disagreed about whether it was wise to operate the camera system so intensively during the early cruise phase. There were also concerns that the brightness of the comet might damage the sensitive optical systems. The spacecraft crossed the orbital path of Mars in mid-November 1978. Then, on December 15th, Voyager 1 finally overtook Voyager 2. From that moment forward, the spacecraft that launched second had become the leading probe. Its name now fully matched its position. Both spacecraft continued making occasional observations of the stars and of the Sun. Most of these measurements were performed for instrument calibration. However, Some useful scientific data was also collected during this phase of the mission. Small system failures continued to appear. A scan platform temporarily froze. A filter wheel in the photopolarimeter became stuck. The plasma experiment showed a gradual decrease in sensitivity. The harsh environment of space was slowly taking its toll on the spacecraft. But the engineering teams on Earth continued to diagnose and solve these problems one by one. Then a more serious issue emerged. This time, the problem appeared on Voyager 2. The spacecraft's primary radio receiver began to malfunction. At one point, Voyager 2 experienced a serious and mysterious malfunction. An unknown failure caused excessive electrical current to flow through the spacecraft's radio receiver system. The surge blew several fuses. For an entire week, all communication with Voyager 2 was lost. Fortunately, the spacecraft had been designed with redundancy. After 7 days without receiving commands from Earth, a timer inside the command computer automatically switched the system to the backup radio receiver. Communication with Voyager 2 was finally restored. However, the news was not entirely good. The primary receiver had been permanently damaged and would never function again. The backup receiver had its own problem. Because of a faulty capacitor in the circuit, it could not properly compensate for Doppler shifts in the radio signal frequency. Correcting for Doppler shifts is essential for communication with a spacecraft moving at high speed. But those shifts are also extremely valuable. They allow engineers to measure the spacecraft's velocity with great precision. Without that capability, the mission team would have to rely on alternative methods of navigation. From that point forward, every transmission sent to Voyager 2 required additional calculations. Engineers on Earth had to carefully determine the exact radio frequency needed for each command. They also had to compensate for the rotation of Earth itself. It was yet another complication, another burden placed on the mission team. If the spacecraft continued to experience failures at this rate, the prospects for a long, extended mission looked uncertain. In fact, internal mission bulletins at the Jet Propulsion Laboratory during 1978 referred to Voyager 2 as a beleaguered spacecraft. One mission engineer later recalled that period as one of the most frightening moments of the entire project. The scariest time was when we lost one of Voyager 2's receivers. Then we discovered that the backup receiver could no longer tune itself to the frequency we were transmitting. That meant we had to learn how to transmit at exactly the right frequency so the spacecraft could still hear us. Fortunately, we eventually figured out how to do it. But for several months it was an extremely stressful period while we tried to understand what had happened and how to work around the problem. In the end, the spacecraft completed the entire mission using what was essentially a receiver that could not properly adjust its own frequency. Despite that limitation, the system worked. Situations like this are common in real space missions. Most people never hear about them. Once the problem is solved, it quickly becomes old news. So far, both Voyager spacecraft had been fortunate. There had been no catastrophic failure. But space is an unforgiving environment. Things can and do break. And sometimes there is no way to repair them. Just in case communication with Voyager 2 was ever permanently lost, engineers prepared a contingency plan. The spacecraft's computer memory was filled with command sequences that would allow it to perform the most basic scientific observations at Jupiter and Saturn, even without further instructions from Earth. Voyager 2 would still carry out a minimal encounter mission. Only 1 year into their journey, both Voyager spacecraft had already consumed about 10% of their hydrazine maneuvering fuel, and this had occurred during the relatively quiet cruise phase of the mission. Whenever the scan platform at the end of the science boom rotates, it transfers a small amount of rotational momentum to the spacecraft body. The hydrazine thrusters must then fire briefly to counteract that motion. These small corrections help keep the spacecraft properly oriented toward its targets. Keeping the spacecraft as stable and properly oriented as possible was a constant challenge. Despite the engineers' best efforts, some degree of drifting and chaotic motion was unavoidable. Voyager carried 2 television cameras. The narrow-angle camera was extremely powerful. Its magnification was about 65 times stronger than normal human eyesight. But that power came with a trade-off. Its field of view covered only about half of a single degree of the celestial sphere. In other words, it was looking at an incredibly small patch of space. The scan platform that aimed the cameras was remarkably precise. But even it had a margin of error. That margin was roughly 1/5 of the camera's already tiny field of view. When that mechanical uncertainty was combined with the small rotational drifting of the spacecraft bus, the result was inevitable. Pointing errors. Engineers calculated that the camera could miss its intended target by as much as 1/3 of its entire field of view. That might not sound like much, but at planetary distances it was significant. It meant that Jupiter, or any other target, would appear to jump around noticeably from frame to frame in Voyager's images. Because of this, extensive post-processing and image stabilization had to be performed on Earth. Only then could scientists assemble the individual frames into smooth moving sequences. The wide-angle camera performed slightly better. It had a magnification of about 8.7 times relative to human eyesight. Its field of view spanned roughly 3 degrees of the sky, making it somewhat more forgiving when pointing errors occurred. On January 4, 1979, Voyager 1 officially entered the observatory phase of the mission as it approached Jupiter. The spacecraft began operating at full capacity. Every day, it performed detailed system scans using its entire suite of scientific instruments. The pace of data collection increased dramatically. Then, on January 30th, the mission entered one of its most intense observation periods. For 4 consecutive days, Voyager 1 focused almost entirely on imaging Jupiter. Pictures were transmitted back to Earth in real time. The spacecraft's camera shutter fired once every 96 seconds. This continued for nearly 100 hours. During that period, Voyager captured images covering 10 full rotations of Jupiter. When played back at high speed, the unfiltered raw images look very different from the beautiful photographs we are familiar with today. They appear rough, grainy, and entirely black and white, which raises an interesting question. If Voyager's cameras were black and white, how did we obtain such vivid color images of Jupiter and its moons? The answer lies in the camera's filter wheels. Much like the photopolarimeter instrument, Voyager's television cameras were equipped with rotating wheels containing several translucent filters. These included green, blue, orange, ultraviolet, and a clear filter. Some of these filters served purely scientific purposes. They allowed only specific wavelengths of light to pass through. By analyzing those wavelengths, scientists could detect the presence of certain chemicals in planetary atmospheres, including sodium and methane. But the filters could also be used for another purpose: color reconstruction. If 3 separate black and white images are taken through different filters, such as green, orange, and violet, those images can later be assigned their corresponding colors on Earth. When the colored images are combined, they produce a synthesized color photograph. This process creates a close approximation of the true color distribution of the planet. In fact, every color image from Voyager is made by combining at least 3 separate monochrome exposures. In some cases, even more exposures were used. In many ways, this method was simply a slower version of the color television system used during the Apollo missions. Apollo's camera performed the same process automatically in real time. Voyager, however, relied on scientists and engineers on Earth to reconstruct the color images after the data had been received. In that sense, post-processing has always been part of the Voyager story. The immense distances involved in transmitting data, the limitations of the spacecraft's pointing accuracy, and occasional system errors meant that Voyager itself could only deliver part of the picture. The rest had to be completed by human hands back on Earth. The work of reconstructing Voyager's images did not end with the original mission team. In many ways, it was only the beginning. Scientists and enthusiasts would spend decades piecing together the full picture from the data Voyager sent back. And that work has continued ever since 1979. Many years later, with the rise of personal computing, a new generation of researchers returned to the Voyager archives. They began unlocking secrets buried inside decades-old raster scans. Using powerful digital processing tools and modern photo enhancement techniques, they brought new clarity to images that had once seemed limited by the technology of their time. Slowly, patiently, they began revealing what Voyager had truly seen. One remarkable example comes from the work of Dr. Mark Showalter. In 1990, while studying 10-year-old Voyager data, he made an unexpected discovery. Hidden within the images was Pan, the 18th and innermost known moon of Saturn. Pan is what scientists call a shepherd moon. It orbits within Saturn's rings, helping maintain the structure of the ring system by gravitationally guiding the surrounding particles. Discoveries like this demonstrate just how much information remained buried in Voyager's data long after the spacecraft had passed its targets. But Showalter was far from the only person contributing to this effort. Over the years, many individuals have dedicated enormous time and skill to restoring and reinterpreting Voyager imagery. People like Brian Burns, Ian Regan, Emily Lakdawala, Björn Jonsson, Ted Strike, and many others. Together with dozens of collaborators, they have stitched thousands of individual frames into enormous panoramas. They have stabilized the spacecraft's drifting images. They have reconstructed moving sequences. And they have added accurate color information using data from both Voyager's cameras and later space missions. Much of this work has been carried out completely independently. Most of these contributors are not affiliated with NASA, the Jet Propulsion Laboratory, or the official Voyager mission. Yet their contributions have become an essential part of Voyager's historical legacy. Their efforts occupy a fascinating space somewhere between science and art. Through careful restoration and digital reconstruction, they have given Voyager's images a second life. The digitization and reinterpretation of these photographs have allowed a new generation of people to experience the mission in ways that were never originally possible. In many ways, Voyager's images have been reborn. By late February of 1979, Voyager 1 had reached the heart of the Jovian system. Jupiter itself dominates that environment, and the largest single feature of the planet is not its storms, or its clouds, or even the famous Great Red Spot. It is Jupiter's magnetic field. Jupiter possesses the most powerful planetary magnetic field in the entire solar system. On the side facing the Sun, the magnetic field extends nearly 7 million kilometers into space. On the opposite side, the field stretches outward even farther. Its magnetic tail extends all the way to the orbit of Saturn. The strength of this magnetic field is staggering. It is roughly 20,000 times stronger than Earth's. This immense field is generated deep inside Jupiter by electrical currents flowing through its outer core. But unlike Earth, Jupiter's core is not dominated by molten iron and nickel. Instead, the key ingredient is hydrogen. Hydrogen is the lightest element in the universe. Under normal conditions, it exists as a gas. But under the extreme pressures found inside Jupiter, hydrogen behaves very differently. It becomes compressed into a liquid form known as liquid metallic hydrogen. In this state, hydrogen conducts electricity. As Jupiter rotates, electrical currents flow through this metallic hydrogen layer. Those currents generate the enormous magnetic field surrounding the planet. Because of this unusual internal structure, Jupiter's magnetic field is produced by a completely different mechanism than the one operating inside Earth. And that field does not exist in isolation. It is constantly shaped and distorted by the solar wind. The solar wind is a continuous supersonic stream of charged particles flowing outward from the Sun. When this flow of particles encounters Jupiter's powerful magnetic field, it pushes against it, compressing the field on the sunward side and stretching it into a vast magnetic tail on the opposite side. The result is a gigantic magnetic structure surrounding the planet. A magnetosphere so large that it dwarfs Jupiter itself. Radiation pressure from the Sun constantly pushes against Jupiter's magnetic field. This interaction between the solar wind and planetary magnetospheres is common among magnetically active planets. But as Voyager 1 traveled through the Jovian system, it encountered something entirely unexpected. Surrounding Jupiter was a massive torus of plasma. This ring of ionized material consisted primarily of sulfur and oxygen ions. It was concentrated along Jupiter's equatorial plane and rotated together with the planet. Scientists now call this structure the Io plasma torus. Because the plasma co-rotates with Jupiter, it distorts the planet's magnetic field. Instead of forming a smooth sphere, the field becomes flattened and stretched into a pancake-like shape. Inside this plasma environment, energetic electrons move through the magnetic field at high speeds. As they spiral along magnetic field lines, they generate powerful radio emissions. These emissions often contain short bursts of intense radiation. At certain frequencies, Jupiter's radio output becomes so strong that it resembles the signal from a cosmic radio pulsar. When we look at Jupiter itself, the scale of the planet is almost impossible to grasp. Aside from its dense core, Jupiter is composed primarily of hydrogen. Between 87 and 92% of the planet's mass is hydrogen. Another 8 to 12% is helium. The remainder consists of methane, ammonia, and trace elements. In terms of size, Jupiter dwarfs Earth. Its diameter is about 11 times larger. Its volume is more than 1,300 times greater, and its mass is approximately 318 times the mass of our planet. Jupiter is classified as a gas giant. Unlike Earth, it does not possess a solid surface. Instead, its atmosphere gradually transitions into deeper and deeper layers of compressed gas. However, scientists believe that far below the visible clouds lies a dense rocky core. From space, Jupiter appears as a swirling tapestry of tans, browns, and oranges. Its upper atmosphere is divided into powerful jet streams that run parallel to lines of latitude. These jet streams create alternating regions known as zones and belts. The lighter-colored zones are rich in high-altitude ammonia clouds. These clouds form when ammonia gas rises and crystallizes in the cold upper atmosphere. The darker bands between them reveal deeper layers of the atmosphere below. The distinctive orange and brown hues come from complex chemical reactions. Material rising from deeper layers interacts with ultraviolet sunlight. Those reactions produce compounds that give Jupiter its characteristic coloration. Jupiter also rotates incredibly fast. A single rotation takes just 9 hours and 55 minutes. That rapid spin contributes to the extreme dynamics of its atmosphere. Where the powerful jet streams meet, enormous vertical storms form along their boundaries. At any given time, dozens of these storms can be found scattered across the planet. But one storm stands above all the others: the Great Red Spot. A cyclone is defined as a large-scale circulation of winds around a central region of low atmospheric pressure. An anticyclone is the opposite. It is a large circulation of winds around a region of high pressure. The distinction is important, because the Great Red Spot is not a cyclone. It is an anticyclone. Anticyclones tend to push clouds outward and clear the central region of moisture. This means the Great Red Spot is not a solid object, or a cloud formation in the usual sense. It behaves more like a gigantic window into the deeper layers of Jupiter's atmosphere. In many ways, it is closer to a hole in the cloud deck than a storm sitting on top of it. Through that opening, scientists can glimpse atmospheric layers that normally remain hidden. The winds around the Great Red Spot are extremely powerful. They can reach speeds of up to 432 kilometers per hour. And this enormous storm has been raging for centuries. Long before Voyager arrived, long before spacecraft ever visited the outer planets, astronomers on Earth were already watching this gigantic scar on Jupiter's face. The winds generated along the edge of the Great Red Spot are extraordinarily powerful. And the scale of this storm is difficult to comprehend. The diameter of the Great Red Spot alone is larger than the entire planet Earth. The first widely accepted observation of the Great Red Spot from Earth-based telescopes occurred in 1831. It was recorded by the German astronomer Heinrich Schwabe. Throughout the 19th century, astronomers continued to observe the feature periodically. However, it may have been seen much earlier. Some historians believe it was already observed in 1665 by the English scientist Robert Hooke. In the first volume of the Philosophical Transactions of the Royal Society, on page 3, Hooke refers to a dark spot located within one of Jupiter's atmospheric belts. It is possible that this reference describes the Great Red Spot, although it could also have been one of Jupiter's 4 large moons, which had been discovered earlier in 1610 by Galileo Galilei. Because of this ambiguity, the precise date of the storm's first discovery remains uncertain. What is not uncertain, however, is what has happened to the storm in modern times. The Great Red Spot is shrinking. Today, it is only about half the size it was during the 19th century. Its future remains unclear. Perhaps it will disappear entirely within our lifetimes. Or perhaps the storm will grow again, entering a new phase of activity. Jupiter itself is a planet of overwhelming scale. Its mass is more than 2.5 times greater than the combined mass of every other planet in the solar system. In fact, Jupiter is so massive that it causes our Sun to wobble slightly. The center of gravity between Jupiter and the Sun lies just outside the Sun's surface. This means that, in a subtle way, the Sun and Jupiter actually orbit each other. As Jupiter radiates heat and energy into space, the planet slowly cools and contracts. Scientists believe Jupiter is the oldest planet in the solar system. When it first formed, it was far hotter and nearly twice as large as it is today. For Jupiter to ignite nuclear fusion and become a star, it would need to be about 75 times more massive than it currently is. That extra mass would raise the temperature and pressure in its core enough to fuse hydrogen. In fact, most stars in our galaxy do not exist alone. Many star systems are binary systems. Some studies suggest that up to 85% of stars belong to systems containing 2 or more stars. Single star systems like our own Sun may actually be the exception rather than the rule. In a different universe, Jupiter might have become a companion star to the Sun, but it never accumulated enough mass to ignite, and so it remained what we see today, a failed star. As Voyager 1 raced past Jupiter, it shifted its attention toward the planet's moons. In 1979, only 14 moons of Jupiter were known. Since then, discoveries made by Voyager, followed by missions such as Galileo, have dramatically increased that number. Today, Jupiter is known to have more than 80 moons, and the number continues to grow as new small objects are discovered. Most of these moons are relatively small. Many are little more than captured asteroids. But 4 of them are very different. These 4 worlds stand apart from the rest. They are known as the Galilean moons. Discovered in 1610 by Galileo Galilei, they remain some of the most fascinating objects in the entire solar system. Each one is a massive world, with its own unique geology and history. Now remember the plasma torus we mentioned earlier? The ring of ionized sulfur and oxygen that distorts Jupiter's magnetic field. Over time, this dense plasma slowly drifts outward. It is pulled away by Jupiter's magnetic field and eventually carried off into space by the solar wind. This raises an important question. If the plasma is constantly escaping, why does the torus continue to exist? Something must be replenishing it. Something within the Jovian system must be continuously feeding material into this ring of plasma. The answer to that mystery was discovered by Voyager 1. And the source turned out to be Jupiter's innermost Galilean moon, Io. When Galileo first observed Io on January 7, 1610, he did not immediately recognize it as a separate celestial body. That realization came the following night. And more than 3 centuries later, Voyager 1 would reveal that this small moon was one of the most violent worlds in the entire solar system. The following night, on January 8, 1610, Galileo confirmed that Io was indeed a separate object orbiting Jupiter. For the next 2.5 centuries, Io remained little more than a faint point of light in astronomers' telescopes. It appeared as an unresolved 5th magnitude object. Small, distant, and mysterious. It was not until the middle of the 20th century that telescopic observations began revealing hints of Io's unusual nature. Spectroscopic analysis of the light reflected from Io suggested something very strange. Its surface appeared to be dominated by evaporite deposits made of sodium salts and sulfur dioxide. This composition was unlike anything seen on our own moon. Io orbits Jupiter at roughly the same distance that our moon orbits Earth. It circles the giant planet at a distance of about 350,000 kilometers above Jupiter's cloud tops. But distance alone does not explain Io's most remarkable feature. What makes Io truly extraordinary is its geological activity. Io experiences enormous tidal forces generated by Jupiter's immense gravity. These forces continuously stretch and squeeze the moon. As a result, its interior is constantly being churned and heated. This tidal heating drives intense volcanic activity. Today, scientists estimate that Io hosts around 400 active volcanoes. Through these volcanoes, the moon ejects enormous amounts of material into space. At least 1,000 kilograms of matter are expelled every second. That is roughly 1 metric ton of volcanic material being thrown into space every second. Once this material escapes Io's surface, it does not simply drift away. The gases are broken apart into atomic ions by radiation and energetic particles. These ions are then captured by Jupiter's magnetic field. They stream away from Io, forming an enormous trail of charged particles behind the moon. The plasma torus surrounding Jupiter is largely composed of this material. It is continuously replenished by the volcanic activity on Io. For the vacuum of outer space, the plasma within this torus is surprisingly dense. It contains roughly 500 atoms per cubic centimeter. That may sound extremely thin compared to Earth's atmosphere, but in interplanetary space, it is remarkably concentrated. The source of Io's intense volcanic activity lies in the details of its orbit. Io does not travel around Jupiter in a perfectly circular path. Instead, its orbit is slightly elliptical. That small eccentricity causes the tidal forces acting on Io to vary continuously. The moon is constantly being flexed. Its interior is repeatedly compressed and stretched. This process generates tremendous internal heat. Normally, tidal interactions like this would eventually smooth out the orbit. Over time, the orbit would become perfectly circular, reducing the tidal heating. But Io's orbit cannot stabilize. 2 other Galilean moons prevent that from happening: Europa and Ganymede. These moons are locked in what astronomers call orbital resonance with Io. Their gravitational interactions occur at regular intervals. Again and again, they tug on Io's orbit. Each encounter slightly disturbs the moon's path. These repeated gravitational pulls keep Io's orbit eccentric. And as a result, the tidal heating never stops. On one side, Jupiter's enormous gravity stretches the moon. On the other side, the gravitational influence of Europa and Ganymede pulls it in different directions. The result is a tortured existence. Io is quite literally being torn apart by gravitational forces. Yet this violent process has a profound impact on the entire Jovian system. Io is also tidally locked to Jupiter. This means the same side of the moon always faces the giant planet. Before Voyager arrived, scientists expected Io's surface to resemble the moon's surface. They assumed it would be covered with impact craters formed over billions of years. Instead, Voyager revealed something completely different. Io's surface is almost entirely free of large craters. The landscape appears young and constantly renewed. It is covered with smooth plains, towering mountains, volcanic pits, and vast lava flows. The surface is painted in vivid colors: yellows, oranges, reds, and blacks. These striking hues are produced by various sulfur compounds scattered across the landscape. During its flyby, Voyager 1 observed at least 9 active volcanoes on Io. Several of them were actually photographed in the middle of erupting. For the first time in human history, scientists were witnessing active volcanoes on another world. Before Voyager, no one even knew such a thing was possible. Before Voyager arrived, the only active volcanoes known in the entire solar system were those on Earth. Then Voyager flew past Io, a moon of Jupiter roughly the size of our own moon, yet it possessed nearly 10 times the volcanic activity of Earth itself. It was a startling realization. For the first time in history, scientists understood that Earth was no longer the most volcanically active body in the solar system. Io had taken that title. As Io moves through Jupiter's powerful magnetic field, something even stranger happens. The moon cuts across Jupiter's magnetic field lines as it orbits the planet. This motion generates an enormous electrical potential. Scientists estimate that about 400,000 volts develop across Io. That electrical potential drives a current of roughly 3 million amperes. The result is a phenomenon known as the Io flux tube. This electric current travels along Jupiter's magnetic field lines all the way down to the planet's upper atmosphere. When the charged particles reach Jupiter's atmosphere, they collide with atmospheric gases. These collisions accelerate electrons and produce an intense, localized glow. Within Jupiter's already permanent polar auroras, this interaction creates a bright spot, a visible mark showing exactly where Io's electrical connection reaches the planet. The incoming particles create what scientists sometimes describe as an electron rain. This constant bombardment contributes to powerful lightning storms within Jupiter's clouds. In other words, Io is not only volcanically active, it is electrically connected to Jupiter itself. And at least in part, Io helps drive lightning in Jupiter's atmosphere. The environment surrounding Jupiter is incredibly hostile. When Voyager 1 passed between Jupiter and Io, it encountered radiation levels that would be fatal to humans. In fact, the spacecraft experienced roughly 1,000 times the lethal radiation dose for a human being. Constant volcanism, extreme radiation, and powerful electric fields. Taken together, these conditions make Io one of the most inhospitable places in the entire solar system. It is not a promising destination for life, so Voyager turned its attention elsewhere, toward another moon, Europa. Voyager 1 did not pass close enough to Europa to capture extremely detailed images. But 4 months later, Voyager 2 would provide a much closer look. Europa has a diameter of about 3,100 kilometers. That makes it slightly smaller than Earth's moon. At first glance, its surface looks completely different from Io's chaotic volcanic terrain. Europa is covered in a vast network of long, dark, crisscrossing lines. These are fractures in the moon's icy crust. The surface is composed primarily of water ice, and it is incredibly cold. Temperatures average around -138 degrees Celsius, which is about -216 degrees Fahrenheit. At such extreme temperatures, water ice behaves very differently. Instead of being brittle like ordinary ice, it becomes as hard as granite. The reddish-brown regions seen across Europa's surface are also made of ice, but they are mixed with darker materials, clay-like minerals, salts, and possibly organic compounds carried upward from deeper layers. Despite its striking appearance, Europa is surprisingly smooth. It lacks the tall mountains and deep impact craters seen on many other moons. In fact, Europa is considered one of the smoothest objects in the entire solar system. Some scientists believe that parts of its surface may be covered with enormous icy spikes, structures that resemble giant stalagmites made of frozen water. On a global scale, the surface of Europa appears to be constantly moving. The cracks and ridges that stretch across the moon's surface show clear evidence of shearing forces. These forces are created by tidal flexing. Just like Io, Europa is stretched and squeezed by Jupiter's gravity, and by the gravitational influence of the other Galilean moons. But there is a puzzle. Europa, like Io, is tidally locked to Jupiter. One side of the moon always faces the giant planet. If tidal flexing alone were responsible for the cracks in Europa's crust, those fractures should form a predictable pattern. A pattern that scientists could easily recognize. Yet when Voyager's images were examined more closely, something didn't quite fit. The fractures on Europa did not match the pattern scientists expected, which suggested something surprising. Something beneath the ice was moving. But the expected pattern of fractures on Europa's surface was not there. Something unusual was happening. The crust itself appeared to be moving, rotating slowly across the surface of the moon, just as tidal forces melt rock inside Io. Scientists began asking an intriguing question. Could those same tidal forces be melting ice inside Europa? Europa's surface contains very few impact craters. This is an important clue. A heavily cratered surface usually indicates an ancient and inactive world. But Europa's smooth appearance suggests that its surface is being renewed over time. Some kind of resurfacing process must be constantly reshaping the crust. Scientists believe the long cracks on Europa behave somewhat like tectonic plate boundaries on Earth. In certain regions, surface material appears to sink downward. In others, new material rises upward to replace it. The leading scientific explanation is that a layer of liquid water, or possibly soft slushy ice, exists beneath Europa's outer shell. This hidden layer may drive the mechanical movement of the moon's icy crust. However, the true size of this subsurface ocean remains unknown, and definitive proof of its existence has yet to be obtained. Unfortunately, even the most conservative estimates present a major obstacle. Europa's solid ice crust may be several kilometers thick. That is far deeper than the deepest holes ever drilled on Earth. For now, reaching this hidden ocean remains far beyond our technological capabilities. Still, scientists continue to imagine what might lie beneath that frozen shell. One day, perhaps, a spacecraft will land on Europa. It might drill downward through the ice, and eventually reach a warm, salty ocean hidden in darkness. An ocean where alien forms of life could potentially exist. There have already been hints that something may be escaping from Europa's interior. Some observations suggest that plumes of water vapor occasionally erupt from the surface, These plumes may form when pockets of pressurized briny water burst through weak points in the ice. If that interpretation is correct, then Europa may be venting material from its interior into space, a process known as cryovolcanism. However, scientists are still uncertain whether these plumes are directly connected to the hypothesized subsurface ocean. When Voyager and later the Galileo spacecraft studied Europa, the possibility of life beneath its ice triggered enormous excitement. For the first time, scientists began seriously considering that life might exist far beyond Earth. Since then, several other moons in the solar system have emerged as potential habitats. Some may even surpass Europa in their chances of supporting life. Yet, Europa remains one of the most compelling targets in the search for extraterrestrial biology. When we think about places where life might exist, we often focus on the so-called Goldilocks zone. This is the region around a star where temperatures allow liquid water to exist naturally. If a planet orbits too close to its star, the heat will cause water to evaporate. If it lies too far away, the water freezes solid. Neither extreme is friendly to life as we know it. Life requires liquid water, so astronomers search for planets located within this narrow habitable zone. Planets in this region are considered promising candidates in the search for life. But discoveries in our own solar system have complicated that picture. Because the source of heat that keeps water liquid does not always have to come from a star. As we move farther away from the sun, temperatures drop dramatically. Yet worlds like Europa may still possess liquid oceans hidden beneath thick layers of ice. And if that is true, then the classic idea of the habitable zone may not be the full story. Life might exist in places we never expected, hidden deep beneath frozen worlds, far from the warmth of any star, farther from the sun. Everything should be frozen, all other things being equal. Worlds located at these distances should contain nothing but solid ice. Yet Europa, a moon of Jupiter far outside the traditional habitable zone, appears to remain partially warm. But the heat keeping Europa active does not come from the sun. Instead, it comes from the immense tidal forces generated by Jupiter itself. Jupiter's gravity continuously stretches and squeezes the moon as it orbits the planet. The gravitational pull of neighboring moons also contributes to this process. Together, these forces pump energy directly into Europa's interior. When a solid object is constantly flexed in this way, stress builds inside it. That stress produces heat. Europa may appear frozen on the surface, but its crust tells a different story. If you look closely at images of Europa's icy plains, you see long fractures running across the surface. Some of these cracks are clearly offset. A ridge that begins in one place suddenly stops. Then it appears again several kilometers away. That discontinuity reveals something important. The surface ice must have moved. It cracked, shifted, and then froze again. If Europa were completely frozen solid all the way through, none of this motion would be possible. Another clue comes from the appearance of the ice itself. Large plates of ice appear broken apart, displaced, and then frozen again in new positions. The pattern resembles something very familiar here on Earth. If you fly over the Arctic Ocean during winter, you see enormous ice sheets drifting slowly across the water. They collide, they crack, they shift, then they refreeze. The surface of Europa shows the same kind of signature. Based on this evidence, most scientists are convinced that beneath Europa's icy shell lies a vast ocean of liquid water. And there is little reason to think that this ocean formed recently. It may have existed for billions of years. On Earth, wherever we find liquid water, we find life. That simple observation makes Europa one of the most intriguing worlds in the solar system. But Europa is not the only remarkable moon orbiting Jupiter. The third Galilean satellite is Ganymede. Ganymede orbits Jupiter at a distance of just over 1 million kilometers. Like Io and Europa, Ganymede is tidally locked to Jupiter. One side of the Moon always faces the giant planet. However, Ganymede's orbital eccentricity is relatively low. Because of this, tidal heating inside the Moon is minimal today. In the distant past, however, things may have been different. Ganymede likely experienced episodes of stronger tidal heating when its orbit interacted more strongly with Io and Europa through orbital resonance. Ganymede holds another extraordinary distinction. It is the largest moon in the entire solar system. In fact, Ganymede is even larger than the planet Mercury. Yet despite its size, it is far less dense. Its mass is less than half the mass of Mercury. This suggests that Ganymede is composed of roughly equal parts rock and ice. Decades after Voyager's flyby, the Galileo spacecraft studied Ganymede in much greater detail during the 1990s. One of Galileo's most surprising discoveries was the detection of a magnetic field surrounding the Moon. A persistent and measurable magnetic field. This observation implies that deep inside Ganymede, something remarkable must still be happening. The Moon's core cannot be completely frozen. Instead, there must still be some internal motion. Some form of conductive material moving beneath the surface. For a body with such a low overall density, that possibility raises fascinating questions about the internal structure of the largest moon in the solar system. For a moon with Ganymede's relatively low density, scientists would not normally expect enough iron in its interior to generate such a strong magnetic field. Yet the observations clearly show that a magnetic field does exist. Even more surprising, Ganymede's magnetic field is not completely stable. It appears to shift and fluctuate over time. Something inside the Moon must be amplifying it. The leading scientific model suggests a possibility similar to what researchers suspect beneath Europa. Ganymede may also contain a vast subsurface ocean. In this scenario, layers of salty water beneath the icy crust could act as an electrical conductor. As that conductive fluid slowly moves, it may interact with Jupiter's magnetic field and generate the magnetic signals detected by spacecraft. Of course, this remains only a theory. Just as with Europa, there is no direct proof yet that Ganymede truly contains a subsurface ocean. But if the saltwater model is correct, the implications would be astonishing. The ocean beneath Ganymede could be enormous. Some models suggest a global layer of liquid water between 100 and 800 kilometers thick. If that estimate is even roughly accurate, it would make Ganymede's ocean the largest in the entire solar system, far larger than all the oceans on Earth combined. There are many competing models for the interior structure of Ganymede. But even if such an ocean exists, it would not be easily accessible. It would lie far below the surface, buried beneath roughly 95 kilometers of ice and rock. Scientists are also uncertain about the origin of Ganymede's unusual surface features. Large portions of the Moon are covered in grooved terrain. These long ridges and valleys bear some resemblance to the cracked, icy plains seen on Europa. That similarity suggests tidal heating may once have reshaped the surface. But this explanation presents a problem. Ganymede orbits much farther from Jupiter than Io or Europa. At that distance, tidal heating should be much weaker. One possible explanation is that Ganymede may have formed closer to Jupiter in the distant past. Later, gravitational interactions could have pushed it outward to its current orbit. Today, Ganymede's surface appears far older than Europa's. It is covered with numerous impact craters left behind by ancient collisions. Radiation from Jupiter's powerful magnetic environment also makes Ganymede a dangerous place. A human standing on the surface would receive a radiation dose strong enough to cause severe illness and death within about 2 months. Before the Voyager missions arrived in the Jovian system, scientists believe that Ganymede and another moon were probably very similar. That other moon was Callisto. Both moons are larger than the planet Mercury. Both appear relatively dark, and both have very low densities, suggesting they contain large amounts of ice. But Voyager revealed that the similarities between them are mostly superficial. Callisto turned out to be a very different world. Voyager 1 showed that Callisto possesses one of the most ancient surfaces in the entire solar system. Its landscape is covered with countless impact craters. These scars were created by meteorite bombardment over more than 4 billion years. And unlike many other worlds, they have remained almost perfectly preserved. Ganymede's surface, by comparison, may be only about 1/4 as old. Callisto shows no clear evidence of internal geological activity. There are no signs of volcanism, no tectonic plate motion, no major resurfacing events. It appears to have remained largely unchanged for billions of years. Its low density once again suggests that large amounts of ice exist beneath the surface. Whether that ice hides a partially molten layer deep underground remains uncertain. Some models propose that Callisto may also contain a salty ocean far below its frozen crust. This idea is based mainly on magnetic measurements. Those measurements suggest that Jupiter's magnetic field may be interacting with a conductive layer inside the Moon. But once again, direct evidence has yet to be found. Jupiter's magnetic field may induce electrical currents inside Callisto. This interaction could imply the existence of a layer of highly conductive fluid beneath the surface. However, the available data is limited, and there is not yet enough corroborating evidence to confirm this interpretation. In fact, it is only one of several competing models attempting to explain the observations. One major challenge to this theory is the absence of tidal heating on Callisto. Unlike Io or Europa, Callisto experiences virtually no tidal flexing from Jupiter's gravity. That means if a thick layer of ice exists inside the Moon, it is likely frozen solid. Some scientists have suggested that radioactive decay of heavy elements deep within Callisto's mantle might provide a source of internal heat. But this raises another question. Is the Moon insulated well enough to trap that heat? Or does it simply escape through the crust and radiate into space? At the moment, we simply do not have enough information to know. Despite these uncertainties, Callisto remains an intriguing exploration target. One important reason is that radiation levels on its surface are far lower than those experienced by the other Galilean moons. For those inclined towards science fiction, or perhaps simply bold ambition, Callisto could even serve as a future base for human exploration. The abundance of water ice on its surface offers enormous potential. That ice could be converted into drinking water, breathable oxygen, and even rocket fuel. As Voyager 1 passed through Jupiter's equatorial region, the spacecraft performed a carefully programmed maneuver. Its television cameras were pointed outward into space, along the planet's equatorial plane, and left exposed for an astonishing 11 minutes and 12 seconds. Such a long exposure was almost unheard of for a deep space mission at the time. NASA was searching for something extremely faint. The squiggly streaks visible in the resulting image are actually stars. They appear as curved lines because their light was recorded for more than 11 minutes. During that time, the spacecraft's natural oscillations and its rapid motion as it flew past Jupiter dragged the points of light across the camera's detector. But the stars were not the true subject of the image. Look closely at the broad band of light cutting diagonally across the center of the frame. That faint structure was the first visible evidence that Jupiter possesses rings. Jupiter's rings are extremely faint. They are composed primarily of thin, dark dust particles. Only one of them, known as the main ring, is even moderately well defined. Scientists believe these rings formed when small meteoroids struck Jupiter's inner moons, blasting streams of fine dust particles into orbit around the planet. The overall age of Jupiter's ring system remains uncertain, But individual dust particles are thought to survive for only about 1,000 years before being removed by various forces, such as radiation pressure and interactions with Jupiter's magnetic field. Because of this, the rings must be constantly replenished by new impacts. Jupiter's rings may be faint and delicate, but they are undeniably real. They must be constantly replenished by new impact events. As dust particles survive in the ring system for only about 1,000 years before being removed by radiation pressure and magnetic interactions. The two Voyager spacecraft dramatically expanded our understanding of the Jovian system. Their observations set the stage for future missions by revealing 3 previously unknown satellites and returning an enormous amount of scientific data. For the first time, scientists could study Jupiter and its moons in extraordinary detail. Despite the technical problems encountered during the early cruise phase, the Voyager mission at Jupiter proved to be an overwhelming success. The results were so impressive that they influenced the direction of another mission that was still underway. At the Jet Propulsion Laboratory, engineers saw an opportunity. In a sense, it was time for JPL to settle an old score. The Pioneer 11 probe, which had already passed Jupiter in 1974, was still traveling outward towards Saturn. Its closest approach to Saturn would occur in September of 1979, only a few months after the Voyager spacecraft had completed their Jupiter encounters and continued on toward the outer planets. Pioneer 10 and Pioneer 11 had originally played a role in the cancellation of the ambitious Grand Tour concept years earlier. Now the situation had changed. JPL and the Voyager team saw a way to use Pioneer 11 to their advantage. Since Voyager 2 was still on a trajectory that could potentially continue the Grand Tour toward Uranus and Neptune, engineers needed to know whether it would be safe for a spacecraft to pass through Saturn's outer ring region. JPL proposed a bold idea. Pioneer 11 should be retargeted to fly through Saturn's outer A-ring. In effect, the spacecraft would act as a pathfinder. If the route proved safe, Voyager 2 could follow it later and continue its journey deeper into the outer solar system. From JPL's perspective, the logic was clear. Pioneer 11 was smaller, less sophisticated, and nearing the end of its primary mission, using it as a test vehicle could reduce the risk for Voyager 2. But the Pioneer team strongly objected. Their spacecraft had its own scientific objectives, and flying too far from Saturn could reduce the quality of the measurements they hoped to obtain. Passing through the outer ring region also carried real danger. Scientists were still uncertain about the composition of Saturn's rings. If the spacecraft encountered larger particles, it could be damaged or even destroyed. Nevertheless, the Voyager team pushed hard for the plan. They argued that the potential reward justified the risk. For the first time in this story, NASA management sided with JPL. Agency leaders agreed that Pioneer 11 had effectively become a prelude to Voyager's larger mission. And so, despite strong objections from the Pioneer team, the decision was made. Amid considerable frustration from Pioneer engineers, NASA's Director of Planetary Programs, Tom Young, announced that Pioneer 11 would indeed pass through Saturn's outer rings. The maneuver would serve less as a purely scientific investigation and more as a reconnaissance mission for the Voyager spacecraft that would soon follow. The Pioneer spacecraft was no longer being treated as a simple trailblazer. In many ways, it had become a test subject, a kind of guinea pig. The Voyager team needed to know whether passing through Saturn's outer ring region was truly safe. The answer would determine whether their extended mission could continue toward the outer planets. Pioneer 11 reached Saturn on September 1st, 1979. During its flyby, the spacecraft came dangerously close to disaster. It narrowly missed a previously unknown moon, passing within just 2,100 nautical miles, roughly 4,000 kilometers. Despite the close call, Pioneer 11 succeeded in discovering another new moon and provided the first detailed measurements of Saturn's magnetic field. Before the encounter, NASA engineers had estimated that the spacecraft had only about a 50% chance of surviving its passage through Saturn's rings. Yet Pioneer 11 crossed the ring plane without suffering any damage. Saturn's rings are enormous. They stretch nearly 300,000 kilometers across space. And yet they are astonishingly thin. Some estimates suggest they are no more than 100 meters thick, about 330 feet. Other estimates place their thickness as low as 20 meters, roughly 66 feet. At the speed Pioneer 11 was traveling, it took less than a single second to pass through the ring plane. Compared to Voyager, Pioneer 11 was a relatively simple spacecraft, but its importance cannot be overstated. It became the first human-made object to reach and study Saturn up close. Saturn itself is tilted about 27 degrees relative to the plane of the solar system. Because of this tilt, the planet experiences seasons. For half of its orbit, sunlight illuminates the northern face of the rings. For the other half, the southern face is illuminated. Saturn takes nearly 29 Earth years to complete one orbit around the Sun, which means each of its seasons lasts about 14.5 years. The rings act like an enormous sundial in space. As Saturn moves along its orbit, the rings cast shifting shadows across the planet's atmosphere. The year 1979 happened to be a special moment in this cycle. Saturn's rings were almost perfectly aligned with the Sun. Because of this alignment, the shadows they cast were minimal. Later missions, especially the Cassini spacecraft decades afterward, would observe Saturn from entirely different angles, revealing far more dramatic views of its rings and their shadows. Meanwhile, the two Voyager spacecraft were racing outward through the solar system. They were traveling significantly faster than Pioneer 11 and would not need 5 years to reach Saturn. Voyager 1, in fact, would encounter the planet just 21 months after leaving Jupiter. Both Voyager spacecraft experienced minor technical issues after their intense encounter with Jupiter's radiation environment. Engineers reported clock errors, occasional photographic artifacts in the imaging system, and brief interruptions in communications. Fortunately, none of these problems proved serious. As the spacecraft moved farther away from Jupiter, they appeared largely unharmed. At one point, engineers attempted to place Voyager 1 into a Sun Canopus alignment, a navigation configuration that used both the Sun and the bright star Canopus to stabilize the spacecraft's orientation. During this maneuver, the star trackers made a mistake. Instead of locking onto Canopus, they briefly locked onto Alpha Centauri. The error caused a temporary loss of the downlink signal. Voyager 2's polarimeter experiment may have suffered permanent damage during the spacecraft's passage through Jupiter's intense radiation environment. Engineers detected a clear malfunction in the instrument's filter wheel. Voyager 1's polarimeter fared even worse. Tests showed that it had lost all sensitivity to light and had effectively become useless. It became the first scientific instrument on either spacecraft to be permanently shut down. Unfortunately, it would not be the last. Meanwhile, Voyager 2's backup mission program remained stored in its onboard computer. This contingency plan had originally been uploaded when the spacecraft lost its primary radio receiver earlier in the mission. Now that Voyager 2 had successfully passed Jupiter, engineers modified that backup sequence to account for the spacecraft's new trajectory. Its secondary receiver continued to function reliably, but engineers at the Jet Propulsion Laboratory remained cautious. The extended mission toward Uranus was beginning to look increasingly realistic. Voyager 1 began its concentrated observations of Saturn in late August of 1980. The spacecraft would pass the planet in November of that same year. Voyager 2, trailing roughly 9 months behind, would follow in 1981. One important discovery was made almost immediately. Using Voyager 1's planetary radio astronomy experiment, scientists were able to measure Saturn's rotation rate. The data showed that the planet completes one rotation roughly every 10 hours and 39.5 minutes. With a small margin of uncertainty, interestingly, Saturn's atmosphere does not rotate uniformly. The equatorial regions can spin as fast as 10 hours and 14 minutes, revealing the presence of extremely powerful jet streams. Saturn may appear calm compared with Jupiter, but appearances can be misleading. Wind speeds in Saturn's atmosphere can reach 500 meters per second, roughly 1,000 miles per hour. The planet's atmosphere behaves almost like a gigantic blender. Violent mixing of gases has smoothed out many of the dramatic color contrasts seen on Jupiter, leaving Saturn with a more subtle appearance. Even so, faint bands are still visible across its cloud tops. Of course, Saturn's most striking feature is impossible to ignore: its rings. Saturn is often called the jewel of the solar system. Galileo Galilei was the first to observe them in the early 17th century, although he did not understand what he was seeing. In his telescope, the planet appeared to have strange protrusions on either side, which he described as arms. Several decades later, the Dutch astronomer Christiaan Huygens correctly identified these structures as rings in the 1650s. Then in the 1670s, the Italian-born astronomer Jean-Dominique Cassini made another crucial discovery. He identified a large gap within the ring system, now known as the Cassini division. Saturn's rings are extraordinarily complex. They are composed primarily of water ice mixed with smaller amounts of carbon-rich material and organic compounds. At first glance, they may appear simple, but the structure of the rings is far more intricate than early astronomers imagined. Some rings are bright and clearly defined, while others are faint and diffuse. In long-exposure photographs, additional rings become visible. Saturn's G-ring and E-ring appear as enormous faint halos of particles encircling the planet, extending far beyond the bright inner rings that dominate most images. Saturn's rings extend far beyond the bright bands most people recognize. The system does not end there. At a distance of roughly 12 million kilometers lies one of the strangest structures in the entire Saturnian system: the Phoebe ring. This ring is named after the small moon Phoebe, whose orbit aligns with the ring itself and from which the ring material likely originates. The Phoebe ring is enormous and extremely faint, almost impossible to see without specialized instruments. It is tilted significantly compared to Saturn's main rings. Even more unusual, the Phoebe ring orbits in the opposite direction of Saturn's rotation and the motion of most of the planet's other moons. Like the moon Phoebe itself, it travels in a retrograde orbit, moving against the normal rotational flow of the Saturn system. For many years, astronomers believed Saturn's rings were ancient remnants left over from the original cloud of gas and dust that formed the planet billions of years ago. In other words, the rings were assumed to be as old as Saturn itself. But this assumption may have been a classic example of what psychologists call the hot hand fallacy. The idea that because something has existed for a long time, it must always have existed that way. More recent observations have challenged that belief. Data from later missions, particularly the Cassini spacecraft that orbited Saturn for more than a decade, to suggest something surprising. Saturn's rings may actually be relatively young. Current estimates indicate they could be less than 100 million years old. That means the rings may have formed long after the planet itself was born, possibly when two or more icy moons collided and shattered, spreading debris into orbit around Saturn. To put that into perspective, the rings may have formed around the same time that dinosaurs still walked the Earth. Even more fascinating, Saturn's rings are not permanent. Material from the rings is gradually being pulled away by the planet's powerful magnetosphere. This process, sometimes called ring rain, slowly drains particles from the rings and sends them spiraling into Saturn's upper atmosphere. At the current rate, Scientists estimate the rings may only survive for another 100 million years or so. In cosmic terms, that is a very short lifespan. For now, however, the rings remain incredibly complex and stable. They are divided into countless narrow bands and structures. Much of this stability comes from the influence of small moons known as shepherd moons. These tiny satellites orbit within or near the rings, using their gravity to keep ring particles confined to narrow lanes. Without these gravitational shepherds, the rings would slowly spread outward and fade into space. The Voyager spacecraft also discovered another strange feature within the rings: dark radial patterns appearing across the bright ring material. These structures were nicknamed spokes. Scientists believe these spokes are caused by interactions between Saturn's magnetosphere and extremely fine dust particles within the rings. Electrical charging can cause these tiny particles to clump together and behave in unusual ways under Saturn's powerful magnetic influence. Saturn itself also presents a striking contrast to Jupiter. Unlike Jupiter's dramatic reddish and orange tones, Saturn appears much more subdued in color. Despite this visual difference, the two planets are actually very similar in composition. Both are dominated by hydrogen gas. Saturn's atmosphere contains roughly 96% hydrogen, compared with about 89% for Jupiter. Saturn contains slightly less helium, around 3.5%. Both planets also contain trace amounts of methane, ammonia, and other compounds. Scientists still debate why Jupiter appears reddish while Saturn does not. One possibility is that Jupiter's colors are produced by chemical reactions in its upper atmosphere involving sulfur compounds or other complex molecules. Another possibility is that solar radiation triggers chemical changes in Jupiter's atmosphere that produce these vivid colors, for reasons that are not yet fully understood. This process appears to occur far less strongly on Saturn. As a result, Saturn's atmosphere appears far more uniform, displaying soft bands of pale yellow and cream-colored clouds rather than Jupiter's intense storms and dramatic color contrasts. Saturn's pale yellowish zones are believed to get their color from clouds of crystallized ammonia high in the atmosphere. Beneath this upper layer, scientists believe there are darker belts and lighter zones similar to those seen on Jupiter. Although they are far less dramatic and much harder to observe, one does not have to travel very deep into Saturn before its hydrogen gas becomes compressed into liquid form. Liquid hydrogen is believed to make up the thickest layer of the planet, accounting for well over half of Saturn's total volume. Deeper still, under enormous pressure, the hydrogen begins to behave in unusual ways. It may transition into metallic hydrogen, a strange state of matter where hydrogen atoms become electrically conductive. In some regions, it may even approach a solid metallic form. At the center of the planet lies a hot, rocky core. Saturn actually emits far more energy into space than it receives from the Sun. In fact, the planet radiates about 2.5 times more energy than it absorbs. Because of the combination of its massive size and its extremely rapid rotation, Saturn is the most flattened planet in the entire solar system. The difference between its equatorial radius and its polar radius is nearly 10%, giving the planet its noticeably squashed appearance. Saturn and Jupiter together dominate the mass of the planetary system. Combined, the two gas giants contain roughly 92% of all the planetary mass in our solar system. Storms do occur on Saturn, although they are typically short-lived and difficult to observe. When they do appear, they often look like bright, milky white disturbances spreading across the otherwise smooth-banded surface of the pale planet. Saturn's powerful winds are responsible for two of the most remarkable atmospheric phenomena anywhere in the solar system. At the South Pole lies a massive hurricane-like vortex, nearly the size of Earth. This storm may have existed for billions of years, and is surrounded by towering clouds rotating around a clearly defined central eye. But Saturn's North Pole reveals something even stranger. There sits a massive hexagonal structure, a geometric storm pattern that appears almost impossible in nature. This hexagon forms a permanent atmospheric cap around the North Pole, giving Saturn one of the most alien-looking features ever observed in the solar system. The shape seems to defy intuition. Nothing like it exists on Earth at planetary scale. However, scientists believe the explanation lies in the complex fluid dynamics of Saturn's atmosphere. Winds at different latitudes move at different speeds. Where these flows interact, instabilities can develop. In this case, the interaction produces a standing wave pattern that stabilizes into a hexagonal shape. Remarkably, scientists have recreated similar structures in laboratory experiments on Earth using rotating tanks of water. By adjusting flow speeds and adding fluorescent dyes, researchers have produced stable polygon-shaped waves that closely resemble Saturn's hexagon. So what first appeared completely alien may actually be a natural consequence of fluid physics. Saturn's magnetic field presents yet another mystery. On both Earth and Jupiter, the magnetic field is tilted relative to the planet's rotation axis by about 10 degrees. This tilt is thought to be a natural consequence of how magnetic fields are generated deep inside planets through the motion of electrically conductive fluids. But Saturn's magnetic field behaves differently. Observations suggest that it is almost perfectly aligned with the planet's rotation axis, something that scientists still struggle to fully explain. Magnetic fields inside planets require motion. Without turbulence and convection deep within a planet's interior, magnetic fields would not exist. The magnetic field is generated by the movement of electrically conductive material, usually liquid metal, deep within the planet. On planets like Earth and Jupiter, the magnetic field is tilted relative to the planet's rotational axis by roughly 10 degrees. Scientists believe this tilt occurs because the dynamo region inside the planet is not perfectly aligned with the planet's outer rotation. Saturn, however, behaves differently. Its magnetic field appears to be almost perfectly aligned with its rotational axis. The tilt may be less than half a degree. This near-perfect alignment is something scientists still struggle to explain. Because of this unusual configuration, Saturn's magnetosphere is somewhat weaker than expected for a planet of its size. Saturn's magnetic field still extends far into space, stretching roughly 600 times the size of Earth's magnetic field. But its strength is slightly lower than many models originally predicted. Saturn is also surrounded by an extraordinary family of moons. Thanks to later missions such as the Cassini orbiter, scientists now know of more moons orbiting Saturn than any other planet in the solar system. At present, Saturn is known to have more than 80 confirmed moons. That does not necessarily mean Saturn truly has more moons than Jupiter. It simply means that our observational data around Saturn has become much more detailed thanks to the Cassini mission. As the Voyager spacecraft raced through the Saturn system, they captured images of several of these remarkable moons. Some of the smallest are the shepherd moons that help maintain the structure of Saturn's rings. Pan, Pandora, and Prometheus orbit within or near the rings themselves. Other moons, such as Janus and Epimetheus, follow nearby paths. These moons are interesting not only because of their unusual shapes and orbital behavior, but also because of the important role they play in maintaining the delicate structure of Saturn's rings. Farther outward lies one of the most recognizable moons in the Saturn system, Mimas. Mimas is believed to play a major role in shaping the Cassini division. The large gap within Saturn's rings, the moon itself is famous for a massive impact crater that dominates its leading hemisphere. This enormous crater gives Mimas an appearance strikingly similar to the fictional Death Star from Star Wars. Moving farther outward, Voyager observed the faint glow of the E-ring. Unlike Saturn's bright main rings, the E-ring appears as a very diffuse outer halo. It is only clearly visible when viewed with the sun shining through the particles. Within this ring orbits a small icy moon called Enceladus. Decades after the Voyager flybys, the Cassini spacecraft would confirm something scientists had long suspected. Enceladus is actively venting material into space. Multiple jets erupt from fractures near the Moon's south pole. These geysers, like plumes, eject warm, salty water into space. The plumes also contain grains of silica sand, nitrogen compounds, and organic molecules, including trace amounts of simple hydrocarbons. The total mass being ejected from Enceladus is extraordinary. The Moon releases roughly 200 kilograms of material every second into space. The Voyager spacecraft only imaged the northern hemisphere of Enceladus and therefore missed these geysers completely. Since most of the activity is concentrated near the South Pole, however, the fact that Enceladus sat directly within the densest region of the E-ring led scientists to suspect that the ring was being continuously supplied by material escaping from the Moon. What no one expected at the time was how significant this discovery would eventually become. The water erupting from Enceladus contains organic molecules, silica grains, and simple hydrocarbons. But perhaps the most important detail is something else. The water is warm. The plumes carry thermal energy, indicating that liquid water reservoirs exist beneath the Moon's icy surface. The source of this heat remains one of the major mysteries of the Saturn system. Tidal heating caused by Saturn's gravity can explain only a small fraction of the energy being observed, perhaps around 10% of the required heat. This raises an intriguing question. Where is the rest of the energy coming from? Enceladus itself is very small. The Moon has a diameter of only about 500 kilometers. Its weak gravity and small size make it unlikely that a large molten core or significant radioactive heating exists deep inside the Moon. Such heat sources may have existed early in Enceladus's history, but they cannot fully explain the level of activity observed today. The mystery remains: how has Enceladus managed to maintain this internal heat for so long? Direct evidence of warm water geysers rising from a subsurface ocean has placed Enceladus near the top of the list of locations where life might exist beyond Earth. In many ways, it has surpassed even Mars and Europa as one of the most promising environments in the search for extraterrestrial life. Moving farther away from Enceladus, Voyager observed another icy world, Tethys. Its surface is covered with impact craters ranging from small pockmarks to enormous basins carved by ancient collisions. Beyond Tethys lies Dione, a rugged moon marked by scars and deep canyons. The trailing hemisphere of Dione is fractured by massive cracks, giving the Moon a broken and weathered appearance. As we continue moving outward through the Saturn system, the moons gradually grow larger. Beyond Dione lies its larger companion, Rhea. Each of these moons appears as an desolate world. Their surfaces record billions of years of collisions with debris, fragments from rings, and wandering objects that have passed through Saturn's gravitational domain. But farther out, the story changes dramatically. Roughly 750,000 miles from Saturn, about 1.2 million kilometers away, lies the largest and most complex moon in the entire Saturn system, Titan. Titan stands apart not only among Saturn's moons, but among all moons in the solar system. For hundreds of years, Titan appeared in telescopes as nothing more than a fuzzy orange sphere. Its thick atmosphere completely hid the surface from view, leaving astronomers with almost no clues about what lay beneath. Titan is the only moon in the solar system with a truly substantial atmosphere. Despite having a surface gravity only slightly weaker than our moon, the atmospheric pressure at Titan's surface is about 1.5 times greater than the air pressure at sea level on Earth. In simple terms, Titan has a lot of sky. Because Titan's gravity is relatively weak, its atmosphere does not cling tightly to the surface the way Earth's atmosphere does. Instead, it forms a thick, extended shell surrounding the moon. Atmospheres gradually become thinner with altitude, which makes it difficult to define where space actually begins. Even on Earth, What most people consider outer space overlaps with layers of the atmosphere. For example, low Earth orbit, where satellites and spacecraft travel, still lies within the outermost layers of Earth's atmosphere. The International Space Station, which orbits within the thermosphere, slowly loses altitude due to this extremely thin atmospheric drag and requires periodic boosts to maintain its orbit. But Titan's atmosphere stretches far higher. The thick orange haze that completely hides Titan's surface exists at an altitude of around 200 kilometers. That is more than twice the height of the commonly recognized boundary of space on Earth, known as the Kármán line, and that haze layer is considered one of the lower layers of Titan's atmosphere. During their brief encounters, both Voyager spacecraft made valuable observations of Titan. However, the Moon's thick atmosphere prevented them from seeing its surface. That mystery would remain unsolved for decades. It would not be until the arrival of the Cassini spacecraft in the mid-2000s that Titan would finally reveal its secret. Attached to Cassini was a small probe named Huygens. When the time came, the Huygens probe separated from the Cassini orbiter and began its descent into Titan's atmosphere. On January 14, 2005, it became the first spacecraft ever to enter Titan's atmosphere and successfully land on its surface. But the mission almost lost a large portion of its scientific data. In an ironic twist of fate, a design flaw in Cassini's radio relay firmware created a serious problem. As Huygens transmitted data during its descent, part of the signal experienced a Doppler shift due to the relative motion between the probe and the orbiter. Because of this unexpected shift, Cassini failed to record a significant portion of the transmitted data stream. The problem that affected the Huygens probe was somewhat similar to the issue that had once troubled Voyager 2. As Huygens descended through Titan's thick atmosphere, it transmitted data through two separate radio channels. However, due to a sequencing error on the ground, the Cassini orbiter was only listening to one of those frequencies. As a result, roughly half of the data transmitted by the Huygens probe was never recorded. Despite these technical problems, combined with a small but costly human error on the ground, the tiny probe still achieved something extraordinary. Huygens returned the very first images ever taken from the surface of Titan. It also provided invaluable measurements of the conditions on this distant and mysterious moon. Titan is an incredibly cold world. At the landing site, the temperature was around 180 degrees below 0 Celsius, nearly 300 degrees below 0 Fahrenheit. And yet, surprisingly, Titan is also a humid world. There are stable bodies of liquid on its surface. Titan has lakes. It has clouds. It even has rain. Titan has weather. Titan has a climate. But the liquid that shapes this world is not water. It is methane. Titan's atmosphere is composed of more than 95% nitrogen, very similar to Earth's atmosphere in that respect. However, the haze and humidity in Titan's atmosphere are caused by methane gas. Methane makes up roughly 1.5% of the atmosphere at higher altitudes, increasing to nearly 5% near the surface. Titan's methane cycle is remarkably similar to Earth's water cycle. Methane evaporates from lakes and seas, rises into the atmosphere, condenses into clouds, and eventually falls again as methane rain. Some of Titan's methane lakes are comparable in size to the Great Lakes of North America. These lakes represent the only stable bodies of liquid known to exist on the surface of any world beyond Earth. Beneath Titan's thick orange haze, wispy methane clouds drift slowly across the sky. Most of Titan's lakes are concentrated near its polar regions. These lakes appear dark and highly reflective in radar images, but they are unimaginably cold. Despite the presence of methane, there is no danger of fire. Titan's atmosphere contains almost no oxygen. making combustion impossible. In fact, Titan holds an astonishing quantity of hydrocarbons. Estimates suggest that Titan may contain hundreds of times more liquid hydrocarbons than all the known oil and natural gas reserves on Earth combined. But unlike Earth's fossil fuels, Titan's hydrocarbons did not originate from ancient life. They formed through purely chemical processes. Ultraviolet radiation from the sun breaks apart methane molecules high in Titan's atmosphere. When hydrogen atoms are stripped away, highly reactive fragments known as methyl radicals are produced. These radicals then combine with one another, forming more complex hydrocarbons such as ethane and propane. Through countless chemical reactions, a vast atmospheric chemistry develops, producing Titan's thick haze and feeding its complex methane-based climate system. Conditions on Titan's surface are also very close to the triple point of methane. This means methane can exist simultaneously as a solid, a liquid, and a gas under Titan's environmental conditions. Even tiny changes in temperature or pressure can cause methane to rapidly change phase. The exact chemical composition of Titan's lakes is still uncertain. Scientists believe they are mixtures containing large volumes of liquid methane along with heavier hydrocarbons such as ethane and propane. It is even possible that solid methane ice, containing trapped nitrogen gas bubbles, could float on the surface of these lakes. However, this idea has not yet been confirmed. Evaporation on Titan occurs extremely slowly due to the Moon's frigid temperatures. However, Titan's thick atmosphere can hold large amounts of methane vapor before rainfall begins. Combined with Titan's low gravity, this may lead to unusual climate cycles. Scientists believe Titan may experience long periods of relative drought lasting decades, or even centuries. These dry periods may then be followed by intense hydrocarbon rainstorms and massive flash floods capable of reshaping the Moon's surface. When Voyager flew past Titan, all we could see was the fuzzy orange sphere you see here. What we now know is that Titan possesses a nitrogen atmosphere about 50% thicker than Earth's. But instead of oxygen, Titan's atmosphere contains methane and other hydrocarbons. And that difference changes everything. Sunlight interacting with methane in Titan's atmosphere triggers complex chemical reactions. These reactions create chains of organic molecules that eventually form the thick orange haze surrounding the Moon. This haze is so dense that Titan's surface cannot be seen using ordinary visible light. For decades, Titan remained an unsolved mystery. Fortunately, the Cassini mission arrived many years later, carrying a powerful radar system capable of penetrating Titan's clouds and haze. Using radar imaging, scientists were finally able to map the hidden surface beneath the atmosphere. What they found was astonishing. Titan truly does contain lakes and seas of liquid methane and liquid natural gas. In many ways, Titan may resemble what Earth looked like billions of years ago, before life had fully developed. Because of its scientific importance, observing Titan became one of the highest priorities for the Voyager 1 mission. In fact, the spacecraft's trajectory around Saturn was carefully designed to allow a close flyby of Titan. But this decision came with a significant consequence. The path required for the Titan encounter meant that Voyager 1 could not continue onward to Uranus or Neptune. This moment marked the point where the journeys of the two Voyager spacecraft began to diverge. Throughout the mission planning process, engineers had considered an alternative option. Voyager 1 could have been redirected away from Titan and instead use Saturn's gravity to launch itself toward Pluto. Had that option been chosen, Voyager 1 would have reached Pluto around 1986. But Titan was considered far more scientifically valuable at the time. As a result, the Pluto mission was abandoned. Pluto would remain unexplored for nearly 3 more decades, until NASA's New Horizons spacecraft finally flew past it in 2015. The decision surrounding Titan was one of the most important moments of the Voyager program. If Voyager 1 had failed to obtain useful measurements or images of Titan, the extended mission for Voyager 2 would likely have been cancelled. Voyager 2 would then have been redirected to perform its own Titan flyby instead of continuing the Grand Tour. Fortunately, Voyager 1's observations of Titan were successful. With Titan studied and the data deemed satisfactory, Voyager 2 was allowed to continue along its original path through the outer solar system. As Voyager 1 departed Saturn, the planet's gravity flung the spacecraft upward, out of the plane of the solar system. From that point onward, Voyager 1 would never again approach another planet. Before leaving the Saturn system, however, the spacecraft captured images of several of Saturn's outer moons. Among them was the strange moon Iapetus, whose surface displays dramatic color contrast. Partly stained by material from Saturn's rings, Voyager 1 also photographed the elusive moon Phoebe, a distant retrograde satellite orbiting far from Saturn. Phoebe moves along a path opposite the rotation of Saturn's other moons and travels within a faint ring that would not be discovered until decades later. For the scientists studying the mission data, the Saturn encounter proved to be extraordinary. Many discoveries were completely unexpected. As researchers continued to analyze the information returned by the spacecraft, it became clear that Saturn was far more complex than scientists had previously imagined. The encounter did not answer every question, but it fundamentally changed our understanding of the Saturn system. The textbooks had to be rewritten. The Voyager flybys provided only a first glimpse of this distant world, but they laid the foundation for future missions, especially the Cassini spacecraft, which would later explore Saturn in far greater detail. By January of 1981, Voyager 1 was already racing away from Saturn and heading toward the outer darkness of interstellar space. Voyager 2, meanwhile, was continuing its journey deeper into the solar system, and its next destination would be something no spacecraft had ever visited before: Uranus. The planetary exploration phase of the Voyager 1 spacecraft had come to an end. No more worlds lay ahead of it. But the mission itself was far from over. Voyager 1 was not shut down. It was not turned off. Instead, the spacecraft continued traveling outward, leaving the known planetary system behind and beginning a new chapter of exploration. It would now study something much larger: our Sun and its interaction with the galaxy. After its encounters with Jupiter and Saturn, Voyager 1 had gained enough speed that the Sun's gravity could no longer hold it in a closed orbit. The spacecraft was now on a trajectory that would eventually carry it out of the solar system entirely. Scientists at the time believed they had a fairly good understanding of what lay ahead. The Sun generates a powerful magnetic field that extends far into space. Charged particles constantly stream outward from the Sun in a flow known as the solar wind. For decades, researchers assumed that this magnetic environment behaved in a way similar to planetary magnetospheres. At some distance from the Sun, the outward-flowing solar wind should begin to slow down and bend backward, pushed by the pressure of the interstellar medium. That pressure comes from the combined radiation and particle winds of other stars throughout our galaxy. In 1981, scientists at the Jet Propulsion Laboratory estimated that Voyager 1 might reach this boundary around 1990. They believed that the crossing would occur at roughly 40 astronomical units from the Sun. That is 40 times the distance between the Earth and the Sun. But the solar system turned out to be far larger than anyone expected. Voyager 1 would not cross this boundary until it had reached a distance of about 122 astronomical units, nearly 18 billion kilometers from Earth, and it would not happen until the year 2012. By that time, an entirely new generation of scientists had taken over the mission. Many of them had grown up with Voyager already flying through space, too young to remember a world before its discoveries. The goal of the Voyager interstellar mission is to study the outermost layers of the Sun's magnetic influence and understand how the solar wind interacts with the surrounding galaxy. Instruments aboard the spacecraft measure the magnetic field and the density of charged particles in space. These measurements reveal how the Sun's magnetic field lines bend and wrap around the outer boundary of the heliosphere, the giant magnetic bubble surrounding our solar system. As Voyager travels farther away, scientists hope to learn just how far the Sun's influence truly extends. But the data did not always behave as expected. At one point, the magnetometer team noticed something puzzling. When Voyager approached the boundary region, the direction of the magnetic field did not change dramatically. If Voyager had truly crossed from the Sun's magnetic domain into interstellar space, the field direction should have shifted noticeably. The lack of change raised a troubling possibility. Perhaps Voyager had not yet left the solar system at all. For a time, scientists debated the meaning of the data. Then another instrument provided the answer. The plasma wave experiment detected oscillations in the surrounding plasma. These waves were triggered by powerful shock waves produced by solar eruptions that had traveled outward through the solar system. When these shock waves reached the region around Voyager 1, they caused the surrounding plasma to vibrate. By measuring the frequency of these oscillations, scientists could determine the density of the plasma surrounding the spacecraft. And that measurement revealed something remarkable. The plasma density was far higher than expected inside the heliosphere. Instead, it matched the density predicted for interstellar space. In other words, Voyager 1 had crossed the heliopause. It had entered the space between the stars. That moment was when scientists finally confirmed that Voyager 1 had entered interstellar space. Researchers and theoretical modelers later revisited the magnetometer data and gradually began to understand why the magnetic field had behaved in such an unexpected way. It turned out that the interaction between the Sun's heliosphere and the surrounding interstellar medium was more complex than scientists had originally assumed. While Voyager 1 was beginning its long journey into interstellar space, Voyager 2 was still deep within the Saturn system. On August 25, 1981, Voyager 2 passed extremely close to Saturn. During part of this encounter, the spacecraft moved through the planet's shadow and temporarily lost communication with Earth. While out of contact, something unexpected happened. Voyager 2's scan platform, the movable structure that carried several of the spacecraft's scientific instruments, suddenly became stuck in a horizontal position. Because communication had been interrupted, the problem was not immediately detected. Once contact with Earth was restored, engineers quickly realized that the situation was serious. The ground team immediately transmitted commands instructing the spacecraft to move the platform away from the Sun in order to protect the delicate optical instruments mounted on it. If the platform had remained pointed toward the Sun, the intense light could have permanently damaged several sensitive sensors. Unfortunately, this malfunction forced the cancellation of several planned observations. Much of Voyager 2's outbound journey from Saturn had to be devoted to diagnosing and troubleshooting the problem. 3 days later, on August 28th, the platform's azimuth actuators began responding again. However, the movement was slow and hesitant. For several weeks, scientific activity on Voyager 2 was reduced, while engineers carefully conducted a series of diagnostic tests. Their analysis suggested that the problem was likely mechanical, possibly caused by lubrication issues or worn gear components inside the scan platform. Despite these setbacks, the Voyager team remained determined to continue the mission's original dream, the Grand Tour. On September 23, 1981, mission planners officially announced that they intended to perform a small mid-course correction maneuver. This burn would adjust Voyager 2's trajectory so that the upcoming Uranus flyby would place the spacecraft on a path toward Neptune. With that decision, the final chain of mission planning was complete. From that moment forward, the spacecraft simply had to survive long enough to reach its next destination. Supporting this extended mission required major upgrades on Earth as well. By the time Voyager 2 reached Uranus, the strength of its radio signal would be only about 1/4 as strong as it had been at Saturn. Even at Saturn, the signal had already been extremely faint. To solve this problem, engineers began combining multiple large radio antennas into coordinated arrays. Several of the massive dishes in NASA's Deep Space Network were also physically enlarged to increase their sensitivity. These upgrades dramatically improved the ability of the network to detect extremely weak signals from distant spacecraft. In fact, the improvements made for Voyager 2 helped transform the Deep Space Network into one of the most powerful radio astronomy systems on Earth. The enhanced antenna arrays could now function as a scientific instrument in their own right. Using these upgraded radio telescopes, scientists have been able to study planets remotely from Earth, even without spacecraft present. This work has led to important discoveries, including evidence of polar ice deposits on Mercury. Meanwhile, engineers continued studying Voyager 2's scan platform malfunction. They eventually concluded that the issue was likely caused by degraded lubrication and worn gear mechanisms within the moving assembly. To reduce further stress on the system, movement of the platform was limited and carefully managed. Even so, the spacecraft remained operational, and the prospects for a successful Uranus encounter still looked promising. What had once seemed like an impossible dream was now becoming reality. A spectacular journey through the outer solar system, something that only a generation earlier had existed purely in imagination, was now unfolding step by step. After traveling billions of miles from Earth, the Voyager spacecraft had already delivered humanity's closest views of Saturn and its magnificent rings. Navigation of the spacecraft relied on extremely precise radio tracking from Earth. By analyzing tiny changes in the radio signals sent between Earth and the spacecraft, engineers could determine Voyager's exact position in space. This information, combined with photographs of Saturn's moons taken against the background of distant stars, allowed mission controllers to refine the spacecraft's trajectory with remarkable precision. And now, with Saturn behind it, Voyager 2 was heading toward a destination no spacecraft had ever reached before. Engineers tracked the spacecraft's trajectory primarily through radio signals sent between Voyager and Earth. By carefully analyzing the timing and frequency of these signals, mission controllers can determine the spacecraft's position with extraordinary precision. This radio data is then combined with photographic measurements. Images of nearby moons are taken against the background of distant stars, allowing scientists to calculate Voyager's exact position relative to known celestial reference points. All of this information is processed together to determine when a trajectory correction maneuver is required. When adjustments are necessary, commands are sent to the spacecraft instructing it to rotate by very precise angles. These rotations allow small onboard thrusters to fire in carefully calculated directions. Voyager uses tiny hydrazine rocket engines to perform these maneuvers. Each of these thrusters produces only a fraction of a pound of thrust. Yet they are sufficient to guide the spacecraft across billions of kilometers of space. So far, the navigational maneuvers have been remarkably precise. The spacecraft's initial launch trajectory was already extremely accurate. As a result, the 230 pounds of fuel carried at launch has proven more than sufficient for the mission. Even after the Saturn encounter, engineers expect that a significant amount of fuel will remain available to continue guiding the spacecraft as it travels outward through the solar system. Beyond Saturn lies the next destination, Uranus. Uranus was not discovered until 1781, when the British astronomer William Herschel recognized that a faint object moving slowly through the sky was not a star, but a new member of the solar system. Before that discovery, Uranus had likely been observed many times throughout history. Ancient astronomers may have recorded it in star catalogues, mistaking the dim moving point for a distant star. When Herschel first identified the object, he actually believed he had discovered a comet. Naming the newly discovered planet soon became a source of controversy. Herschel himself proposed naming it after King George III of Britain. For many years, several English scientific institutions referred to the planet as Georgium Sidus, meaning George's star, outside of Britain. However, this name was deeply unpopular. A German astronomer named Johann Bode suggested a different name, Uranus. By the middle of the 19th century, even the last English institutions still using Herschel's original name finally adopted the new designation, Uranus. Uranus is also one of the few planets whose rings can be observed from Earth, although detecting them requires advanced instruments. Interestingly, the rings of Uranus were discovered in the same year that Voyager 2 was launched. In 1977, astronomers observing Uranus from a flying observatory operated by NASA noticed something unusual. As Uranus passed in front of a distant star, the starlight dimmed several times before and after the planet itself blocked the light. These brief drops in brightness revealed the presence of narrow rings surrounding the planet. Uranus soon revealed another extraordinary feature. It rotates on its side. Most planets in the solar system rotate around axes that are roughly aligned with the original spinning disk of gas and dust from which the solar system formed. Venus is an exception. It rotates backward compared with most planets, possibly due to tidal forces or a massive impact early in its history. But Uranus is stranger still. The planet is tilted dramatically, with its rotational axis lying almost completely sideways. Uranus, along with its rings and moons, is tilted by about 98 degrees relative to the plane of its orbit around the Sun. In effect, the planet rolls around the Sun like a ball rather than spinning upright like the other planets. Uranus orbits the Sun along the same general plane as the other planets, known as the ecliptic. However, its rotational axis is dramatically tilted. The current scientific consensus suggests that this unusual tilt was caused by a massive impact early in the planet's history. During the formation of the solar system, hundreds of planetesimals condensed out of the protoplanetary disk surrounding the young Sun. What followed was a chaotic period of collisions and gravitational interactions. In many ways, it resembled a cosmic game of bumper cars. Bodies collided, merged, shattered, and were thrown into new orbits as they competed for space within the forming solar system. At some point during this violent era, Uranus may have suffered a glancing collision with a large planetary body. The impact could have knocked the entire planet onto its side. Evidence supporting this idea comes from the orbits of Uranus's moons. They travel along the planet's tilted equatorial plane, suggesting that they likely formed after the collision or from debris created by the impact. Modern models of solar system formation suggest that the giant planets did not originally form exactly where they are today. Instead, after their formation, the outer planets likely migrated through the solar system. Gravitational interactions between Jupiter and Saturn may have triggered a dramatic rearrangement of the planetary orbits. This event may have pushed several planets outward into the distant regions where we see them today. Some models even suggest that Uranus was once the outermost planet of the solar system. During this chaotic period of orbital migration, Neptune may have moved outward and eventually past Uranus, taking its place as the most distant major planet. Evidence for this planetary migration appears in multiple forms. Computer simulations of early solar system dynamics reproduce similar orbital changes. Geological records also provide clues. The surface of Earth's moon contains evidence of a period known as the Late Heavy Bombardment. During this time, the inner solar system experienced a surge of impacts from asteroids and debris. Many scientists believe this bombardment may have been triggered when the migrating outer planets scattered large numbers of icy bodies inward toward the Sun. Some theories go even further. It is possible that the early solar system once contained additional planets that no longer exist here today. rather than being destroyed. These planets may have been completely ejected from the solar system by gravitational interactions with the giant planets. If so, they would now wander the Milky Way as rogue planets, dim and cold objects drifting alone through interstellar space. In that sense, our cosmic neighborhood may once have included worlds that are now lost forever. Today, Uranus orbits the Sun at an average distance of about 19 astronomical units. Because its orbit is slightly elliptical, that distance varies between roughly 18 and 20 astronomical units. In terms of kilometers, Uranus lies about 2.6 billion kilometers from the Sun. At that distance, the planet takes just over 84 Earth years to complete a single orbit around the Sun. Meanwhile, Uranus spins once on its unusual axis every 17 hours and 14 minutes. Because of its extreme tilt, Uranus experiences some of the most unusual seasons anywhere in the solar system. Each pole receives continuous sunlight for about 42 Earth years. That long period of daylight is then followed by 42 years of complete darkness. When Voyager 2 finally encountered Uranus in January 1986, the spacecraft observed a pale blue world that appeared almost completely featureless to Voyager's cameras. Uranus looked like a smooth sphere with very little visible activity. Later image processing techniques, including artificial color enhancement, revealed that there were subtle brightness differences across the planet's atmosphere. But at the time, Uranus appeared to be a strangely quiet and almost lifeless world. Modern observations using more advanced telescopes have revealed that Uranus is more dynamic than Voyager first suggested. As the planet slowly moves around the Sun, changes in its atmosphere become visible. Several clouds have been detected, some of which may persist for decades. When studied at wavelengths beyond visible light, Uranus reveals far more structure than early images suggested. The key to understanding Uranus's unusually calm appearance lies deep within the planet itself. Unlike the other giant planets, Uranus produces very little internal heat. Jupiter, Saturn, and Neptune all radiate significant energy into space. But Uranus barely emits any excess heat at all. As a result, atmospheric motion on Uranus is much weaker than on the other giant planets, giving the planet its strangely quiet appearance. Temperatures within Uranus's atmosphere can drop as low as 49 Kelvin in Fahrenheit. That corresponds to roughly 371 degrees below zero. 49 Kelvin is only 49 degrees above absolute zero, making Uranus one of the coldest planetary environments in the entire solar system. This extreme cold may provide further evidence for a violent event in the planet's distant past. A massive collision early in Uranus's history could have caused the planet to lose much of its original internal heat as it was disrupted and later reassembled. Another possibility is that some type of internal barrier exists inside the planet, preventing heat from the core from efficiently reaching the outer layers of the atmosphere. Like Jupiter and Saturn, much of Uranus is believed to consist of thick layers of hydrogen in both gaseous and liquid forms. However, deeper inside the planet, the structure likely becomes very different. Scientists believe that Uranus may contain a mantle composed of exotic forms of ice. Under the immense pressures inside the planet, substances such as water, methane, and ammonia exist not as familiar frozen solids but as dense, high-pressure fluids. Beneath this mantle lies a relatively small rocky core. Interestingly, only a tiny amount of methane in Uranus's upper atmosphere is responsible for the planet's distinctive color. Less than 3% methane is enough to absorb red wavelengths of sunlight and reflect blue light back into space, giving Uranus its pale bluish appearance. Strangely, the region high above the atmosphere tells a different story. The thermosphere of Uranus can reach temperatures close to 850 Kelvin. That is hundreds of degrees hotter than the deeper atmospheric layers below. Exactly how this heat is maintained remains one of the unsolved puzzles of the planet. Measurements of solar radiation, magnetic field activity, and other possible heat sources do not come close to explaining why the upper atmosphere is so hot. Uranus's magnetic field adds yet another layer of mystery. Not only is the magnetic field tilted dramatically, nearly 60 degrees away from the planet's rotational axis, it also appears to be offset from the planet's center. The field strength is highly uneven as well. In some regions, it is nearly 10 times stronger in the northern hemisphere than in the southern hemisphere. This unusual geometry suggests that the processes generating the magnetic field inside Uranus may be very different from those operating inside Earth or Jupiter. One possibility is that the magnetic field is generated by convection occurring much closer to the planet's surface than previously expected. Another hypothesis proposes that Uranus may possess a more conventional internal magnetic field, but that the field is partially redirected or distorted by materials located deeper inside the planet. One substance that might influence magnetic behavior under extreme pressure is carbon. Deep within Uranus, carbon atoms could be compressed into unusual forms. Under such extreme conditions, carbon may crystallize into diamond. Some scientists have proposed that enormous quantities of diamond could form inside Uranus's interior. These diamonds might grow into massive structures, perhaps even the size of mountains, before slowly drifting upward through the planet's interior layers. The idea of gigantic floating diamonds, sometimes called diamond bergs, remains speculative, but it represents one of several attempts scientists have made to explain the strange and puzzling behavior of Uranus's magnetic field. The truth is, we simply do not know the full explanation. Voyager 2 remains the only spacecraft that has ever visited Uranus. Unfortunately, it was not equipped with the extremely sensitive and sophisticated instruments that would be required to fully understand the interior of this distant ice giant. It is important to remember that many of the more exotic explanations proposed by scientists are not direct observations. They are scientific hypotheses. These ideas represent possible explanations for the strange measurements Voyager recorded. But they remain only one possibility among many. Often, the most dramatic and exciting explanations attract the most attention. But in science, human expectations must always be tempered by caution. The universe frequently turns out to be more subtle than our imaginations suggest. Voyager 2's trajectory during the Uranus encounter also created unique observational challenges. Unlike its flybys of Jupiter and Saturn, where the spacecraft passed along the plane of the planet's moons, Voyager 2 approached Uranus almost directly along its rotational axis. In other words, the spacecraft would plunge through the orbital plane of Uranus's moons rather than travel alongside it. Because of this geometry, the time available for close observations was extremely limited. Voyager 2 had only about 5.5 hours to collect its most valuable data. During earlier encounters with Jupiter and Saturn, the spacecraft had enjoyed observation windows lasting 30 hours or more. At Uranus, the situation was very different. The spacecraft would pass close to many of Uranus's moons almost simultaneously. There would be no time to slowly observe one moon after another as Voyager moved through the system. Instead, every instrument had to work continuously, gathering as much information as possible in a very short period of time. Voyager 2 reached its closest approach to Uranus at approximately 10 o'clock in the morning on January 24, 1986. For a brief moment, humanity had its first close look at one of the most distant planets in the solar system. But just 4 days later, on January 28th, another event would capture the attention of the entire world. An event completely unrelated to Voyager, yet one that would overshadow this remarkable achievement. On that morning, the Space Shuttle Challenger prepared for launch on its 10th mission. Designated STS-51L, Everything appeared normal as the countdown reached its final moments. Then, just after liftoff, something went terribly wrong. A plume of flame appeared near one of the shuttle's solid rocket boosters. The powerful engines responsible for providing most of the thrust during launch. Moments later, the entire vehicle was engulfed in a massive explosion. The shuttle Challenger broke apart in a catastrophic fireball, sending debris spiraling down toward the Atlantic Ocean. All 7 astronauts aboard were lost. The tragedy shocked the world. The disaster occurred during the same week as Voyager 2's historic flyby of Uranus. Any attention that might have been focused on this extraordinary planetary exploration suddenly disappeared as the United States and much of the world mourned the loss of the Challenger crew. At the time, the Space Shuttle program was only 5 years into operational flights. Following the accident, all shuttle missions were suspended for nearly 3 years while investigators examined the causes of the disaster and safety procedures were redesigned. Meanwhile, far beyond Earth, Voyager 2 continued its silent journey. Uranus lies so far from the Sun that sunlight reaching the planet is extremely faint. And yet, in that distant darkness, the spacecraft was revealing a new world for the first time in human history. Uranus lies so far from the Sun that sunlight there is roughly 400 times dimmer than it is near Earth. Because of this extremely low light level, Voyager's cameras must keep their shutters open much longer in order to capture useful images. However, the spacecraft's scan platform was not designed for perfectly smooth motion. Instead of moving in one continuous fluid sweep, the platform adjusts in small, stepwise movements, alternating between elevation and azimuth. Elevation, azimuth, elevation, azimuth. Because of this mechanical limitation, the platform cannot maintain a perfectly stable lock on a celestial object during long exposures. If it attempted to do so, the resulting images would likely appear smeared or blurred, especially considering the small pointing errors already present in the scan platform itself. To overcome this challenge, several operational changes were introduced for the Uranus encounter. One of the most important involved using the spacecraft's gyroscopes and attitude control system in a new way. Instead of relying solely on the scan platform for pointing, the Voyager team decided to use the spacecraft's hydrazine reaction control thrusters to assist with target tracking. In other words, rather than moving only the instrument platform, engineers would carefully rotate the entire spacecraft itself to help keep the cameras aligned with their targets. This approach required more fuel, but the mission team considered the risk worthwhile. After all, this would be humanity's only opportunity to observe Uranus up close. At this immense distance, radio communication also became a major challenge. Radio signals traveling at nearly the speed of light still required about 2.5 hours to reach Earth from Voyager. Commands transmitted from Earth required the same amount of time to reach the spacecraft. Every decision had to be carefully planned in advance. As Voyager 2 approached Uranus, the spacecraft began capturing a series of long-exposure images of the distant planet. Among its early observations were views of the planet's narrow epsilon ring. Because Uranus is tilted dramatically on its side, Voyager observed the rings almost face-on rather than from the side. The spacecraft also took images of the 5 major moons that were known at the time: Miranda, Ariel, Umbriel, Titania, Oberon. Unlike the moons of most other planets, the moons of Uranus follow a unique naming tradition. Rather than being named after figures from Greek or Roman mythology, they are named after characters from the works of William Shakespeare and the poet Alexander Pope. This unusual convention reflects the English origins of Uranus's discovery. Most of Uranus's moons are relatively small and very dark. The largest, Titania, has a diameter of less than 800 kilometers. making it less than half the size of Earth's moon. Today we know that Uranus has at least 27 natural satellites. However, these 5 moons remain the most significant. Scientists believe that many of these moons may have formed from debris produced during the massive collision that likely tilted Uranus onto its side. This shared origin may explain why many of the moons display similar compositions and surface characteristics. Among them, the innermost and smallest of the 5 is perhaps the most unusual: Miranda. Despite its small size, Miranda displays one of the strangest landscapes in the entire solar system. Closer inspection reveals a surface that appears fractured, distorted, and dramatically reshaped. Enormous cliffs tower above vast canyons. When scientists measure the difference between the highest peaks and the deepest valleys on Miranda, they find some of the most extreme vertical relief anywhere in the solar system. This tiny moon, with a total surface area slightly smaller than that of Saudi Arabia, contains cliffs and chasms that dwarf many geological features found on much larger worlds. The surface clearly records an ancient history of impacts, with craters scattered across much of the terrain. And yet, something else must also have shaped this world. Some other geological process must have been at work. One possibility is that Miranda experienced tidal heating in the past. If its orbit was once more elliptical than it is today, gravitational interactions with Uranus could have flexed the moon's interior, generating heat. That heat may have partially melted the moon's interior and reshaped its surface. This raises an intriguing possibility. Could Miranda once have experienced cryovolcanic activity? Could icy material have erupted from beneath the surface, reshaping the landscape we see today? The truth is, we still do not fully understand what happened there. The thing is, we simply do not know. Voyager 2, the only spacecraft ever to have visited Uranus, is not equipped with the kind of highly sensitive and sophisticated remote sensing instruments that would be required to fully unlock the secrets of the ice giant's interior. It is important to remember that many of these exotic claims, while scientifically valid possibilities, are not observations in themselves. They are merely one of many potential explanations for the measurements we have obtained. Often, the most exotic and exciting possibilities receive far more attention than the seemingly mundane ones. Human expectations are difficult to temper, especially when the unknown invites speculation. Because Voyager 2 is passing Uranus almost directly along the planet's rotational axis, the geometry of the encounter is very different from the flybys of Jupiter and Saturn. Instead of traveling along the plane of the moon's orbits, the spacecraft will cut directly through that plane. As a result, the time Voyager 2 has available to make observations is extremely limited. During the Uranus encounter, the spacecraft will have only about 5.5 hours for detailed observations, whereas during previous planetary encounters, it sometimes had 30 hours or more. Voyager 2 will reach its closest approach to nearly all of Uranus's moons at almost the same time. It will not be able to move gradually from one moon to another while traveling outward. Instead, it must collect as much data as possible in a very short window of opportunity. The near encounter with Uranus occurs at 10 o'clock in the morning on January 24, 1986. Just 4 days later, on January 28th, an unrelated event will capture the world's attention and overshadow this remarkable exploration. The launch signal had been given, and everything appeared to be proceeding normally up to a minute before liftoff. Then the shuttle Challenger began powering up its main engines. Go with throttle up. Go throttle. Moments later, a catastrophic explosion appeared to originate from one of the solid rocket boosters that provided most of the power during launch. Instead of separating as planned, the entire spacecraft vanished in a massive fireball. The shuttle Challenger disintegrated and fell back toward the ocean in spiraling debris. The mission, STS-51L, broke apart during ascent. killing all 7 crew members aboard. This tragedy occurred during the same week as Voyager 2's flyby of Uranus. Whatever attention the flyby might have received quickly faded as the nation mourned the loss of 7 astronauts. The shuttle program, only 5 years into its operational life, was placed on a hiatus that lasted nearly 3 years. Uranus lies so far from the Sun that light levels there are roughly 400 times dimmer than they are near Earth. To capture useful images in such darkness, Voyager's cameras must keep their shutters open for much longer periods of time. The spacecraft's scan platform does not move in one smooth, continuous motion. Instead, it operates through incremental adjustments in both elevation and azimuth. Because of this design limitation, it cannot maintain a perfectly steady lock on a celestial object for an extended period. If it attempted to do so, the result would likely be a blurred image. This limitation becomes even more problematic when considering the small pointing errors that already exist within the scan platform itself. To address these challenges, several operational changes were made specifically for the Uranus encounter. One of the most important changes involved intentionally using the gyroscopes within Voyager's guidance system. The Voyager team also decided to use the spacecraft's hydrazine reaction control jets to assist with target tracking. Instead of relying only on the scan platform, they would carefully rotate the entire spacecraft. This method consumed far more fuel, but the Voyager team believed the risk was worth it. After all, this would be humanity's only chance to see the 7th planet and its moons up close. Radio signals from this distance, traveling near the speed of light, take about 2.5 hours to reach Earth. Commands sent from the ground require the same amount of time to reach the spacecraft. Voyager captures a series of long exposure images as it approaches Uranus, including remarkable views of the planet's Epsilon ring. Because of the extreme tilt of Uranus, the spacecraft is imaging the ring almost head-on. During the encounter, Voyager also observes and studies as much as possible of the 5 known Uranian moons at that time. These moons are Miranda, Ariel, Umbriel, Titania, and Oberon. The naming convention for Uranus's moons is unique among the major bodies in the solar system. Rather than being named after figures from Greek or Roman mythology, they are named after characters from the works of playwright William Shakespeare and poet Alexander Pope. This tradition dates back to the planet's distinctly English history of discovery. The moons themselves are relatively small and extremely dark. The largest moon, Titania, is less than half the size of Earth's moon and has a diameter of under 800 kilometers. Today we know that Uranus has at least 27 natural satellites, but these 5 remain the most significant. Scientists believe that these moons likely formed after a massive impact event that may have tipped Uranus onto its side. This could explain the remarkable similarities observed among them. The smallest and innermost of these moons, Miranda, is perhaps the most fascinating. Despite its tiny size, Miranda possesses an incredibly chaotic surface. Closer inspection reveals that dramatic reshaping of its surface has occurred over time. If one measures the distance between the highest peaks and the deepest valleys on Miranda, the results are astonishing. This tiny moon, whose total surface area is slightly smaller than that of Saudi Arabia, contains some of the tallest cliffs and deepest canyons anywhere in the solar system. Its surface appears extremely ancient, with impact craters scattered almost everywhere. Yet the landscape also suggests that some other geological process must have been active at some point in its history. One possibility is tidal heating in the past, when Miranda's orbit may have been far more eccentric than it is today. Another possibility is that Miranda may once have experienced cryovolcanism. These questions remain unresolved. Voyager 2 raised them when it observed this tiny moon in detail for the first time. And, so far, it has been the only spacecraft ever to do so. Only a future dedicated mission could truly answer them. The people working in the spaceflight operations facility represent only one small part of the massive effort required to keep Voyager 2 operational. Many others, far from the cameras, continue to support the mission. Like all space projects, Voyager is the result of a vast collaborative effort. When the Uranus encounter ends late next month, Voyager 2 will continue its journey toward the 8th planet from the Sun, Neptune. The people you see here will still be here, carefully watching over their spacecraft. Voyager's encounter with Neptune will bring planetary exploration to the end of its first great phase. This phase represents humanity's initial reconnaissance of the outer solar system. Although missions like Mariner, Viking, and Voyager have taught us an enormous amount, there is still far more left to learn. The engineers who operate these spacecraft and the scientists who analyze their data have become our teachers. Very recently, the Planetary Science and Astrobiology Decadal Survey, published every 10 years, recommended to NASA and the United States Congress that the next large flagship robotic mission should focus on Uranus. This mission could be developed sometime before the year 2032. Unlike Voyager 2, which simply flew past the planet, the proposed mission would be an orbiter. It would resemble a mission like Cassini, large, sophisticated, and capable of making detailed measurements while remaining in orbit for an extended period of time. Uranus occupies a unique position in planetary science today. It is considered a high-priority exploration target. It is very likely that we will see a dedicated mission to Uranus within our lifetimes, although the process has only just begun. Any meaningful results from such a mission may still be decades away. These decadal surveys represent the collective views of research institutions and academic communities. They provide critical guidance for policymakers and for those responsible for funding scientific missions. However, their recommendations are not guarantees. Only time will determine whether these ambitious plans are ultimately approved and funded. Uranus's orbit was first calculated in 1783 by the mathematician Pierre-Simon Laplace. Over the following decades, astronomers noticed irregularities in the planet's motion. These irregularities could not be explained unless another large body existed beyond Uranus. In 1841, the English mathematician and astronomer John Couch Adams began calculating where this unknown planet might be located. At the same time, without knowing of Adams's work, the French mathematician Urbain Le Verrier was independently reaching the same conclusion. By 1846, Le Verrier believed he had calculated the precise position of this mysterious object. Adams's calculations had already caused a frenzy among British observatories, which began searching the night sky for the predicted planet. Adams had provided 6 possible locations where the planet might be found. Le Verrier, however, narrowed the prediction to a single point. He published his results in August of 1846. Le Verrier was not particularly well liked at the Paris Observatory. His intense ambition and relentless drive for efficiency had earned him many rivals. Yet his calculations would soon lead to one of the most remarkable discoveries in the history of astronomy. Unpopular, frustrated, and increasingly desperate, he wrote to Johann Gaillet, director of the Berlin Observatory. On September 18th, when the letter arrived just 5 days later, Gaillet decided to search for the new planet that very same evening. That night, he found it within 1 degree of the predicted position. Like Uranus before it, the object had previously been seen by telescopes but had been mistakenly classified as a star. Observations made over a period of 4 days clearly revealed its proper motion, and Neptune was officially confirmed as a planet. In a sense, it was a German discovery based on a French calculation. Despite having been observed earlier by telescopes, no one had recognized Neptune as a planet. It is so faint and so distant that it cannot be seen under ordinary conditions. Its existence was entirely unknown to ancient cultures and civilizations. The successful prediction and discovery of Neptune demonstrated that Isaac Newton's laws of gravitation apply across enormous cosmic distances. As Voyager 2 travels farther and farther away from the Sun, it gradually loses its ability to navigate using sunlight alone. From Voyager's perspective, our star simply grows dimmer with every passing day. Because of this, Voyager 2 increasingly relies on its cameras to send back attitude information. These images are long exposures designed specifically to reveal distant stars. Nearly 100 photographs are taken of the region of space between Saturn and Uranus for the purpose of optical navigation. Even more images are captured during the long journey from Uranus to Neptune. As Voyager 2 approaches Neptune, the spacecraft takes several long exposure photographs in the planet's direction. Imperfections and noise within the images are carefully removed. The natural rotation of the spacecraft is accounted for, and each point of light is catalogued. Any point of light that moves between frames, more than expected from spacecraft rotation alone, is classified as a potential newly discovered moon. Out here, sunlight is extremely weak. Because of this, the camera shutters must remain open for much longer than they would near Earth. The Voyager ground team has to become extremely creative in the way they manage the spacecraft's motion. Voyager was never designed to completely eliminate all angular momentum. There are simply too many moving parts within the spacecraft for that to be possible. Even small internal events, such as the starting and stopping of the tape recorder on board, can produce tiny impulses. Over long periods of time, these small impulses accumulate and gradually affect the spacecraft's rotation. To compensate, engineers implement software changes to reduce scan platform motion and improve the response of the gyroscopes. These adjustments are critical for stabilizing the spacecraft during the long exposure imaging required at such great distances. Compensating for the spacecraft's rotation becomes one of the central challenges faced by the Voyager ground team. By the late 1980s, light levels at Neptune are only about 40% of what they are at Uranus. Overall, Neptune appears roughly 900 times dimmer than Earth when viewed from Voyager's cameras. Such darkness requires extremely long exposure times, which in turn increases the risk of image smearing. This smearing poses a serious threat to Voyager's ability to gather reliable optical data, and capturing clear photographs is absolutely essential. In many ways, it is the primary purpose of the mission. For that to happen, the Voyager team must ensure that the spacecraft remains as stable as possible while its cameras collect these precious images. Keeping the spacecraft stable is not an easy task when it is racing through completely unexplored space. Voyager 2 encounters Neptune in August of 1989. This would become the spacecraft's final planetary encounter. After Neptune, the exact trajectory of the probe would no longer matter very much. Because of this, the ground team performs a mid-course burn in 1987, carefully positioning the spacecraft so that it will pass above Neptune's north pole and fly close to its largest moon. Triton, unlike Jupiter, Saturn, or Uranus, Neptune has only one truly major moon. Triton contains roughly 99% of the total measured mass of all objects orbiting Neptune. The other 13 known satellites are extremely small, resembling irregular asteroid-like bodies. Triton itself is smaller than Earth's moon, but it is far colder. Surface temperatures reach nearly 390 degrees below 0 Fahrenheit. It is so cold that nitrogen freezes directly into solid ice, forming the bright polar cap visible on Triton's surface. The white cap near the South Pole is composed primarily of frozen nitrogen, but the dark streaks across the surface tell a very different story. Those streaks are created by geysers that erupt from beneath the surface and deposit dark material across the ice. During the Voyager flyby, scientists detected 2 active geysers. This was astonishing. Here was a world so cold that even nitrogen exists as ice. And yet it was still geologically active. Time and time again, Voyager forced scientists to rethink what they believed they understood about the outer solar system. It changed our understanding of planets, rings, magnetic fields, and moons. The mission created a legacy of discovery that continues to guide many future explorations of the outer planets. Unlike Uranus, Neptune has a fairly typical axial tilt. Because of this tilt, the planet experiences seasonal variations similar in principle to those on Earth. However, the scale of time involved is extraordinary. Neptune requires roughly 164 years to complete a single orbit around the Sun. Like the other giant planets, Neptune does not have a solid surface. Instead, it consists of multiple internal layers where pressure and temperature increase dramatically with depth. As you move inward, matter transitions through different phases under immense pressure. There are several ways scientists can measure the rotation of a planet like Neptune. One method involves mapping the structure of the planet's magnetic field and determining how quickly it rotates. However, the rotation of the magnetic field does not always match the rotation of the atmosphere. Since there is no visible solid surface, the atmosphere becomes the primary reference point. But even the atmosphere does not rotate at a single uniform speed. Rotation varies depending on latitude. Near Neptune's equator, the atmosphere completes a full rotation in roughly 18 hours. The planet's magnetic field, however, appears to rotate once every 16 hours. Another important difference between Neptune and Uranus is the amount of energy they radiate into space. Neptune emits a surprisingly large amount of internal heat. This extra energy powers an extremely dynamic and active weather system. Although Neptune is only slightly more massive than Uranus, its atmosphere appears far less hazy. Cloud structures and massive storm systems can be clearly observed. Like Uranus, Neptune's outer atmosphere is composed primarily of hydrogen and helium. The ratio is roughly 80% hydrogen and 20% helium. A small amount of methane gas in the upper atmosphere absorbs red light and reflects blue wavelengths. This is what gives Neptune its deep blue color. Neptune's upper atmosphere is also slightly more transparent than that of Uranus, allowing scientists to observe more detailed cloud structures within its turbulent skies. Uranus, as we now know from further study, actually possesses cloud features and atmospheric banding that are almost identical to what we observe on Neptune. A higher concentration of methane in the upper atmosphere, combined with a thinner layer of icy haze, likely results from the greater internal energy present on Neptune. These conditions produce the deeper, darker blue color of Neptune and allow more atmospheric details to become visible. The bright white clouds that appear across Neptune's atmosphere are most likely concentrations of methane ice particles. During its flyby, Voyager 2 observed several large circular storm systems. The largest of these became known as the Great Dark Spot. Much like Jupiter's Great Red Spot, this feature is an anticyclone, a massive region of high pressure. It appears as a dark opening in the atmospheric haze, revealing deeper and darker layers below. However, unlike Jupiter's Great Red Spot, which has persisted for hundreds of years, Neptune's Great Dark Spot proved to be far more temporary. When Neptune was imaged again by the Hubble Space Telescope in 1994, the Great Dark Spot had completely vanished. Since then, other similar storm systems have appeared in different regions of the planet. This suggests that Neptune's circular storms have relatively short lifespans but form regularly. The exact mechanism that causes these storms to form and dissipate is still not fully understood. Neptune also possesses the fastest winds of any planet in the solar system. These winds are even faster than the transonic jet streams observed on Saturn. Near Neptune's equator, powerful westward jet streams move against the planet's eastward rotation. These winds have been measured at nearly 600 meters per second, or roughly 1,300 miles per hour. Neptune may be about 50% farther from the Sun than Uranus and receives only about 40% as much solar energy. Yet, despite receiving less sunlight, Neptune's internal heat plays a crucial role in driving its extreme weather. Energy rising from deep within the planet powers the fastest and most dynamic planetary winds in the entire solar system. Neptune's gravity also plays a major role in shaping the distant region beyond its orbit. This region is known as the Kuiper Belt, a vast field of icy objects located just outside Neptune's path around the Sun. Neptune's gravitational influence helps maintain the overall structure of the Kuiper Belt. Without Neptune's presence, many of these icy bodies might have gradually merged together to form a distant frozen planet. Several dwarf planets reside within this region. Objects such as Orcus, Haumea, and Pluto are all part of the Kuiper Belt. Their early development was likely influenced by the later arrival of Neptune into this region of space. Scientists now believe that Neptune did not originally form at its current distance from the Sun. Instead, it migrated outward during the later stages of solar system formation. As Neptune moved outward, its gravity reshaped the Kuiper Belt and scattered many objects into new orbits. The Kuiper Belt that exists today is enormous. In fact, it is nearly 20 times larger than the asteroid belt located between Mars and Jupiter. The Kuiper Belt is nearly 20 times larger than the asteroid belt and is home to some of the strangest and most ancient celestial bodies in the solar system. In another completely unexpected discovery, Neptune's magnetic field turned out to behave in a very unusual way. Much like the magnetic field of Uranus, Neptune's magnetosphere is tilted at an extreme angle relative to the planet's axis of rotation. Even more surprising, the magnetic field does not appear to be centered within the planet. Instead, it is offset from the center by nearly half of Neptune's radius. An even more extreme displacement than what scientists observed at Uranus. Originally, researchers believed that Uranus's strange magnetic field might be the result of the planet's sideways orientation. But Neptune shows the same phenomenon despite having a much more typical axial tilt. This suggests that the explanation must lie somewhere deep inside both planets. Some internal process within the ice giants must be generating this unusual and highly distorted magnetic field structure. Voyager 2 also conducted detailed observations of Neptune's largest moon, Triton. Triton is a very unusual satellite. Not only does it orbit Neptune in the opposite direction of the planet's rotation, but its orbit is also significantly tilted relative to Neptune's equator. Because of these unusual orbital characteristics, scientists believe that Triton did not originally form around Neptune. Instead, it was likely captured by the planet long ago. Mathematical models suggest that Triton is slowly spiraling inward toward Neptune. Far in the distant future, it may eventually cross Neptune's Roche limit. When that happens, the Moon would be torn apart by tidal forces, forming a spectacular ring system before the remaining material ultimately falls into Neptune's atmosphere. The surface of Triton is extraordinarily diverse. Voyager revealed landscapes unlike anything previously seen in the solar system. There are circular depressions, rugged ridges, massive impact basins, craters, smooth plains, frozen deposits, and a strange terrain that scientists refer to as cantaloupe terrain because of its distinctive texture. How could a moon develop such a complex and dynamic surface? One possible explanation is cryovolcanism. This process involves eruptions driven not by molten rock but by volatile materials such as water, methane, or ammonia. Instead of lava, these eruptions release icy slurries or gases that reshape the landscape. Voyager 2 found that roughly 55% of Triton's surface, at least the portion that could be directly imaged, is covered in frozen nitrogen. In this respect, Triton bears some similarities to Pluto. However, Triton appears to lack the dark, reddish hydrocarbon material that gives Pluto its distinctive coloration. It is important to note that one entire hemisphere of Triton remained completely unobserved during the Voyager flyby. Even more intriguing, telescope observations of Triton made during the 1960s suggested that the Moon reflected far more red light than it did when Voyager 2 finally flew past it in 1989. This raises an interesting possibility. The appearance of Triton's surface may have changed over time. Seasonal processes, frost cycles, or geological activity could have altered the surface in ways that scientists are still trying to understand. The appearance of Triton may have changed considerably over time. Cryovolcanic activity could have altered its surface during the decades between telescope observations and the Voyager flyby. It is even possible that Triton may look very different today compared with the images captured more than 30 years ago. When Voyager 2 photographed Neptune with the Sun positioned behind the planet, it made another unexpected discovery. Just as it had during its earlier planetary encounters, the spacecraft revealed new rings that had never been seen before. The images that revealed these faint rings required extremely long exposure times. Some exposures lasted 591 seconds. By earthly photographic standards, that is an extraordinarily long time. It represents nearly 10 uninterrupted minutes of collecting light from one of the most distant planets in the solar system. As Voyager 2 begins to move away from Neptune in 1989, the planetary phase of its mission comes to an end. Like its twin spacecraft, Voyager 1, it now begins what scientists call the interstellar phase of its mission. For the remainder of its operational life, Voyager will continue observing our Sun from ever greater distances. It will map and measure the Sun's magnetic field in the same way it previously studied the magnetic fields of the giant planets. Each Voyager spacecraft also carries something unique. Mounted to the side of the probe is a gold-plated 12-inch phonograph record. The record is enclosed inside a protective case and includes a small stylus designed to read the information recorded on its surface. These records are known as the Golden Records. Their origins can be traced back to an earlier pair of spacecraft, Pioneer 10 and Pioneer 11. An English journalist named Eric Burgess believed that the Pioneer probes, which were themselves destined for interstellar space, should carry a message from humanity. He presented this idea to a well-known NASA advisor. That advisor was a professor at Cornell University and director of its Laboratory for Planetary Studies, Dr. Carl Sagan. During the 1970s, Carl Sagan would become one of the most recognizable science communicators in the world. He was also a strong advocate for the scientific search for extraterrestrial life. In his advisory role for NASA, he gained significant influence over the direction of American robotic space exploration. Sagan was deeply inspired by the idea that spacecraft leaving the solar system could carry a message from Earth. He successfully persuaded NASA to include a small, lightweight plaque on both Pioneer spacecraft. For the Voyager mission, Sagan expanded the concept much further, borrowing several symbolic elements from the Pioneer plaques. The covers of the Voyager records were designed to function as a set of instructions. If an alien intelligence were ever to discover the spacecraft, these diagrams would explain how to play the record and interpret the information stored within it. In essence, the cover acts as a blueprint that could allow another civilization to unlock the message contained in the Golden Record. Carl Sagan himself was never certain that the record would ever be found, but he believed that sending such a message into the galaxy was a meaningful gesture. It was humanity's way of announcing that we existed, and that we were curious enough to reach beyond our own world. Carl Sagan was never formally considered a member of the Voyager mission team, and the Golden Records themselves did not contribute directly to the spacecraft's scientific objectives. Even so, his influence over NASA's broader planning and communication efforts was significant, and at times somewhat controversial. In truth, very few scientists expect that the Voyager Golden Records will ever actually be discovered and read. From a cosmic perspective, The Voyager spacecraft are extremely small and incredibly difficult to detect. They emit no significant radiation, and they are many orders of magnitude smaller than even a modest asteroid. What the golden records truly represent is something else entirely. They are a thoughtful attempt to design a system of communication that is free from cultural or biological assumptions. The challenge facing Carl Sagan and the Golden Record team was profound. How do you communicate complex ideas to an intelligence that shares no cultural background with you at all? How would an alien civilization even understand the concept of time? They would have no reason to recognize a second ox, a minute, or an hour. Because of this, the Golden Record designers relied on universal constants. They used numbers and measurements derived directly from the fundamental structure of the cosmos. One of the most important symbols on the Golden Record cover appears in the lower right corner. It shows two hydrogen atoms, each consisting of a single proton and a single electron. In the diagram, the hydrogen atom on the right is shown with its electron facing outward, while the other atom shows the electron facing inward. In a neutral hydrogen atom, at its lowest energy state, the proton in the nucleus and the electron in its outer shell spin in opposite directions. In other words, their spins are anti-parallel. However, if a small amount of energy enters the system, perhaps from a collision with another atom or from incoming radiation, the electron can move into a slightly higher energy state. In this excited state, the spin of the electron becomes aligned with the spin of the proton in the nucleus. The two particles are now spinning in the same direction. Eventually, that extra energy must be released. When this happens is unpredictable, governed by the probabilistic rules of quantum mechanics. At some random moment, the electron will suddenly drop back to its lower energy state. When it does, a small amount of energy leaves the atom in the form of radiation. This radiation appears as a radio wave. These emissions from hydrogen atoms occur naturally throughout the universe. They can be detected almost everywhere. They are not tied to any particular planet, star, or astronomical event. They are truly universal. On the Golden Record cover, a line drawn between the two hydrogen atoms represents a wavelength of 23 centimeters. This wavelength serves as the fundamental unit of time and measurement used throughout the entire diagram. All of the other symbols on the cover are expressed in binary form using this universal reference. Many people have explained the Golden Record diagrams in far greater detail than I can here, and I encourage you to explore those explanations as well. The information engraved on the cover outlines a step-by-step process that explains how to play the record and interpret its contents. The first side of the record is relatively simple. It contains music, greetings spoken in many human languages, and recordings of natural sounds from Earth. The second side of the record is far more complex. It contains a sequence of encoded information designed to communicate images and data about our planet and our species. These tones are separated by a clearly audible beep. Each tone actually represents an image encoded within an audio signal. The pitch of the tones corresponds to brightness values, while the timing of the tones corresponds to the position of each point in the image. The images were designed to be displayed on a classic standard definition cathode ray tube television. Each image contains 512 lines of resolution. Every line lasts 8.3 milliseconds. Each full image requires approximately 4.2 seconds of audio. Because the record is recorded in stereo, two audio channels play simultaneously. This allows two streams of information to be transmitted at the same time. Using modern digital tools, researchers such as Ron Barry have followed the instructions engraved on the Golden Record cover. By doing so, they were able to successfully decode the information hidden within Side B of the record. Their work demonstrated that the encoding method still functions correctly even today. Of course, The chances that an alien civilization will ever encounter Voyager are extraordinarily small. For almost every measurable reason, such a discovery is extremely unlikely. Even if another intelligence did discover the spacecraft, there is no guarantee that Carl Sagan and his team's attempt at communication would actually succeed. What the Golden Record truly represents is something deeper. It serves as a conceptual framework that future generations of humans can build upon. In many ways, it was the method of communication that mattered more than the record itself. The approach was the real experiment. The first successful interplanetary mission carried out by humanity was NASA's Mariner 2 spacecraft, which flew past Venus in 1962. Voyager 2's historic flyby of Neptune occurred in 1989. In just 27 years, humanity managed to fly past, orbit, or land on every planet in the solar system. During that short span of time, we completed the first preliminary reconnaissance of our planetary neighborhood. There is only one moment in history when such a transformation happens. It is the moment when a species first leaves its homeworld and begins exploring the surrounding cosmic environment. It is an extraordinary privilege to be alive during that first moment. Consider how many objects we now know exist within the solar system that were completely unknown before these missions began. Many worlds that once appeared as nothing more than faint points of light suddenly revealed detailed landscapes and complex environments. Before spacecraft exploration, we had almost no idea what their surfaces looked like. In many cases, our earlier assumptions turned out to be completely wrong. The Voyager and Viking missions fundamentally changed our understanding of the solar system. Not so much in the basic celestial mechanics of planetary motion, which we already understood fairly well, but in nearly every other way. Before these missions, our knowledge of the solar system was incredibly limited. In many respects, it was almost prehistoric. The true era of detailed knowledge about our planetary system began between 1975 and 1989. During that short period, humanity saw these distant worlds clearly for the first time. And among all those worlds, including the dozens of moons that orbit the giant planets, entirely new chapters of planetary science were opened. Among all the worlds that the two Voyager spacecraft explored, as Dr. Stone mentioned, we have found no evidence of life. There are hints and early signs suggesting that complex organic molecules may be forming in some environments, but there is not a single piece of evidence that life exists anywhere else in the solar system. Not even the smallest indication. For me, that realization only emphasizes how rare and precious the Earth truly is, and how extraordinary the life that exists upon it must be. Thanks in part to Carl Sagan. Another historic moment occurred in February of 1990. At a distance of about 40 astronomical units from the Sun, Voyager 1 turned its cameras back toward the inner solar system. It captured a tiny, faint point of light suspended in the darkness. That point of light was Earth. The photograph would later become known as the pale blue dot. It was the final image of our planet ever taken by the spacecraft before its camera system was permanently shut down. For me personally, the Voyager mission carries a special meaning, not because I was ever involved with it, but because of when it happened in my life. As a child, the Voyager encounters with the outer planets helped shape my understanding of our place in the solar system. I was too young to fully appreciate the flybys of Jupiter and Saturn, but I clearly remember the encounters with Uranus and Neptune. I remember seeing the images on the evening news and being amazed by what humanity was accomplishing in space. For the first time, we were seeing these distant worlds in extraordinary detail. It felt as if we were among the first people in history to truly see them. Many others who were born in the 1970s may remember that same feeling. Voyager 1 was actually launched after Voyager 2, but it was placed on a faster trajectory. Today it is the most distant human-made object from Earth. It travels through space at a speed of roughly 38,000 miles per hour. Nothing humanity has built is expected to ever catch up to it. Voyager 2 travels slightly slower, at roughly 34,000 miles per hour. Even so, that speed is still about 40 times faster than the speed of sound on Earth. The Voyager spacecraft are still functioning today. In many ways, they are like elderly explorers continuing their journey far from home. I like to think of them as twin sisters, aging but still working. Over the years, each spacecraft has experienced different technical problems, yet both remain alive. As their nuclear power sources slowly decay, the available electrical power continues to decline. Because of this, engineers have gradually shut down instruments and heaters one by one. Today, the spacecraft operates the largest object ever built by humanity. At the time this video was produced, it was located about 156.5 astronomical units from the Sun. That is more than 156 times the distance between Earth and the Sun. Radio signals from Voyager 1 take roughly 21.5 hours to reach Earth. Scientists expect that the spacecraft will continue operating until they reach distances of roughly 200 astronomical units sometime in the early 2030s. Both Voyager probes have far exceeded the expectations that engineers originally had for them. Their discoveries transformed our understanding of the solar system. The data they collect continues to inspire new generations of scientists. It also inspires artists, writers, and anyone who looks up at the night sky and wonders what lies beyond. These two small robotic explorers represent some of the best qualities of humanity. They carry with them our curiosity, our courage, and our desire to understand the universe. Their journey is still continuing, and the history they created will remain with us for generations to come.